Amazing team of Amity Institute of Click Chemistry and Research Studies, I, Dr. Shruti Khanna Ahuja, extend a warm welcome to all the dignitaries and esteemed guests, our Honorable Founder President Sir, Dr. Ashok K. Chauhan, Honorable Chancellor Sir, Dr. Atul Chauhan, Honorable VC Ma'am, Professor Dr. Balvinder Shukla, respected Dr. W. Silvamurthy Sir, Director General ADSI and President of Amity Science, Technology and Innovation Foundation, ASTIF, and he's also the Chancellor of Amity Chhattisgarh. Respected Professor Chandradeep Tandon Sir, Additional Pro Vice Chancellor, Dean Faculty of Biosciences and Biotechnology. Dr. Richa Pandey, she's the HR Head at Amity University. Respected Professor Mona Lisa Mukherjee, Director AICCRS. Our eminent speakers, Professor Hiroyuki Furuta from Kyushu University, Japan. Professor Shankar Prasad Rath from Department of Chemistry, IIT Kanpur. Dr. Kuntal Manna, Associate Professor from Department of Chemistry, IIT Delhi. Professor Deepak Chopra from Department of Chemistry, IISA Bhopal. All the esteemed guests, faculty members, scholars, and dear students, to the one-day International Symposium on Bioinorganic Chemistry, Structure, Function, and Applications, ISBIC-2025. The lighting of the lamp signifies the acknowledgement and blessings. We begin our symposium with the lighting of the lamp accompanied by an invocation dedicated to this light in our lives. In this regard, I request all our esteemed guests to kindly come forward so that we can have a lamp lighting ceremony. Thank you so much for that beautiful rendition. As a tradition at Amity, we welcome our guests with a bouquet of flowers. In this regard, may I request Silvamurthy sir and Dr. Mona Lisa ma'am to please come forward and welcome our guests with a bouquet of flowers. May I first invite on stage Professor Hiroyuki Furuta sir to please come ahead. Please put your hands together to welcome sir. May I now request Professor Shankar sir to please come on the stage. Please put your hands together to welcome him. May I now invite Dr. Kuntal Manna to please come on stage. Please put your hands together to welcome Dr. Manna. May I request Professor Deepak Chopra sir to please come ahead. So I request all our guests to kindly grace the dais and unveil the abstract book. Thank you so very much. May I now humbly request Dr. W. Silvamurthy sir, President, Amity Science, Technology and Innovation Foundation, ASTIF, to motivate us and shower his blessings upon us. Before I invite him, I would like to run a brief bio sketch about him. Dr. Silvamurthy is presently working with Amity University as President of Amity Science, Technology and Innovation Foundation, also Director General for Amity Directorate of Science and Innovation and Chancellor of Amity University, Chhattisgarh. He has served the Defense Research and Development Organization, DRDO, which comes under Ministry of Defense, Government of India, for close to 40 years in various leadership positions. He superannuated from DRDO in 2013 as Distinguished Scientist and Chief Controller, Research and Development, Life Sciences and International Cooperation, and joined Amity University thereafter in his present role. At DRDO, serving in various senior leadership roles, he was responsible for the research and development of all the health-related and life science-related technologies that were inducted in the armed forces with the sole aim to keep the armed forces healthy and efficient in all operational environments, including extremely inhospitable terrains. At Amity University, Dr. Silvamurthy has been an instrumental in augmenting the research, science and innovation research activities at Amity University since his joining the organization in 2013 for making Amity a research and innovation-driven university. He has been involved in facilitating research activities such as building collaboration for research and development at the national and international levels, commercialization of technologies developed by scientists and researchers at Amity University, guiding and promoting the faculty and researchers for developing the 5 Ps, which are projects, PhDs, publications, patents, and products. With this glorious biosketch and with deep respects, I would like to invite Sir to enlighten us with his thoughts. Please put your hands together for him.
Thank you. My dear students, very distinguished guests on the dais, off the dais, and all those who have joined us in this program, on behalf of Founder President, Dr. Ashok K. Chauhan ji, and also the Chancellor, Dr. Atul Chauhan, Vice Chancellor, Dr. Balvinder Shukla, and on behalf of everyone in Amity fraternity, I extend a very, very warm welcome to each and every one of you. It's a very happy occasion today that Amity is going to add yet another major facility to our infrastructure, R&D infrastructure, which is NMR, nuclear magnetic resonance with 400 megahertz. And it's one of the powerful system which you'll be using it for characterization of new materials. And you can see the whole synthesis process, right from the raw materials to the products, including byproducts. So it's a very, very unique facility which Amity has invested along with the Government of India through a FIST project. So on this occasion, I must compliment Dr. Mona Lisa Mukherjee, who is one of the star performer among the various faculties over here, a great achiever, a person who is committed, devoted, and all the time so passionate about research, innovation, and building people, building institution. So Mona Lisa, congratulations to you on this great recognition. Let's give a big clap to her. Because this is her effort to bring this system, the FIST, through the FIST project, where Amity has invested equally with the Government of India. And I'm sure it will be a national facility, not only for Amity, but we will also give the services to other institutions who may be less fortunate not to have this. So, but we will provide this facility at a national level. So this is a very, very important milestone today. We must put on record our gratitudes to Honorable Founder President, Dr. Ashok Chauhan ji, and also Chancellor, Dr. Atul Chauhan ji, who is President of our Educational Foundation, for this patronage and also the support, guidance, inspiration, motivation they provide to Amity Research and Innovation Ecosystem and to all our researchers here. So we put on our gratitudes on record and then convey our best wishes for and seek continued support from them as well. So I'm so happy to welcome very distinguished guests, Professor Hiroyuki Furuta. He is from Kyushu University, Japan. And so he has been in this field of bioinorganic chemistry for quite a long time, and he is in the chemistry field. He is very well known in Japan and the whole world today. And so you have traveled all the way from Japan. Thank you so much, Professor Furuta, for being with us. I hope you will have a fruitful stay here. And also we will look at how do we connect with you, with your university, and to take forward our collaboration by your presence here. We are also very fortunate to have a very distinguished professor, Professor Shankar Prasad Rath, who is from Indian Institute of Technology, Kanpur. I was there just about a month ago on an occasion of Dr. Ashutosh Sharma, who was former secretary, DST, who is from Amity University, Indian Institute of Technology, Calcutta, Kanpur. And then on that occasion, I was able to meet some of the distinguished professors. So he is from, Shankar Prasad Rath is from such a great institution. And I'm sure that his presence, his coming over here, will open up new avenues for collaboration with you, with IIT Kanpur. So we will take forward this collaboration. I'm sure Mona Lisa and all the faculties here will take forward this connectivity. We are also fortunate to have Dr. uh, Kuntal Manna, and he is from IIT Delhi, and he's our neighbor. The closest IIT is IIT Delhi, and I'm sure that we will have more occasion to work together. He's already collaborating with Mona Lisa Mukherjee in many ways, and also our other faculties. So certainly we will expand, deepen our relationship with Dr. Manna. And we are also happy to have Professor Deepak Chopra from ISER. And this is also a great institution which deals with both education, science education and research. And he is one of the outstanding scientists, Deepak Chopra. Because as soon as I remember Deepak Chopra, the name which comes to my mind is the person who wrote the quantum healing, who talks about, he's a doctor, medical doctor, but then he has worked on curing many terminal illness through quantum. So quantum healing is his field, and but then this this Kuntal this Deepak Chopra is different, and I'm so happy that he is here, and he is also an icon in the field of chemistry. So we have such very distinguished faculties and also scientists who have assembled today on this occasion of NMR facility, which will be inaugurated in the evening, but then to deliberate on a very important theme, bioinorganic chemistry. And so its application is structure characterization and functions and so on. So this symposium, international symposium, since we have international representatives here in person as well as online who have been invited to join, this symposium is looking at what are the biological applications of inorganic chemistry in the biological field. That is why it is bioinorganic chemistry. Because you have the organic chemistry, biochemistry, but then now it is bioinorganic chemistry. So specifically focusing on how does inorganic chemistry like metalloporphyrins, for example, or the metallochemistry, how can it be applied in the biological system, new drug development, new molecule synthesis. So all this is going to be deliberated. So I'm so happy that this theme has been rightly chosen, because there are a lot of application coming from the inorganic molecules getting application in the biology. Now coming to the facility, NMR facility 400 megahertz, and this is founder president. You will be happy to know the founder president of Amity Education Group is also in the field of chemistry. He did his master's in chemistry from Meerut University, and then he went to Germany to do his doctorate in chemical engineering. So he went to Germany, and he stayed there for 28 years. And then he became the largest non-European investor in the field of the research and development, engineering, construction, every field of engineering related, polymer chemistry, polymer technology, every domain. He became an icon in the field yeah, globally by his presence, 3 decades of presence in the Germany. He employed more than 8,000 Germans and other nationals on his payroll. So that is our founder president. So he is also in this field of chemistry. So I'm sure he will be also addressing and interacting with you at some point of time. And I'm sure he is observing the program, because in spite of all this, the other schedules which he have, which is almost 18 hours a day, but he still finds time for such event. Founder President, welcome. And then grateful to you for this kind blessing, support, guidance, patronage to research and innovation. And we look forward to your continued blessings to all of us. And this facility is specifically, we express our gratitudes to you. And our Chancellor, Dr. Atul Chauhan, is also a very well educated and very dynamic, charismatic young leader who is driving the Amity Education Group as the president of our Ritanand Balve, the Education Foundation. He has 2 degrees, one in engineering, the other one is in the management. So he has the engineering degree from University College of London and also the management from London School of Economics. So he is our chancellor, and he gives complete support. He recently announced a quantum mission, Amity quantum mission, where he immediately at the seed 20 crores have been, he has assured to provide 20 crores for the Amity quantum mission, which will be aligned to the national quantum mission. So such kind of support is there for research and innovation in Amity Education Group. So we are so grateful to all the trustees for their support. We have many missions happening here. Like one is, I said, quantum mission. We are looking at quantum computing, quantum sensing, quantum communication, quantum materials, and metrology. So all these domains, Amity is now, we have 70 faculties working in quantum alone. So this is one mission. We have space mission. Amity Space Mission. We are working with the Indian Space Research Organization. We are applying artificial intelligence for space application. So this is yet another mission which we have. We have a green hydrogen mission because green energy is a focus. So we have a big mission, green hydrogen, which is again, we are going to have a center of excellence from Ministry of New and Renewable Energy Source. And we also have the other important mission is defense technology mission. So these are very important missions which Amity is driving with the blessings of founder president and the chancellor. And I'm so happy that this click chemistry is contributing in almost all domains, every system, all pervasive. So my compliments to Dr. Mona Lisa Mukherjee and the whole team of faculties like Saikat Datta, Ranjan Patra, and all the faculties whom I see here. So let's give a big compliment to these people over here, the faculties. The whole click chemistry was established when Dr. John Moses from Nottingham University visited here. And then at that time, founder president invited him and he said, why don't we start a Amity Institute of Click Chemistry? So that was born on the visit of Dr. John Moses, which is now in Cold Spring Harbor Research Institute in US, in the Eastern Coast near Long Islands. And then over that, this institution has been built. We have electrochemistry, we have click chemistry, and a lot of products have come, like nano hydrogel, which has been developed by Dr. Mona Lisa, which is finding an application in deep wound healing, diabetic wound healing. So she has developed using this click chemistry. Sodium ion battery is being pursued here. So we have a very strong electrochemistry and the battery group, which is working on sodium ion battery. And we also have the bioinorganic chemistry, because she has a lot of application in biological, which she will be mentioning. Now, coming to briefly about Amity Research, and I will conclude in 2 minutes. Amity is a research and innovation driven university. We have 12 universities in India, 18 campuses abroad, 28 schools. We have 250,000 students, 10,000 faculties, 5,000 PhD scholars. So we have whole system is driven towards research and innovation. Even curriculum design, pedagogy, method of delivery is to promote creativity, innovation, problem-solving ability. So in this direction, we have filed more than 2,600 patents, and we have published 45,000 research papers. Our H index is 194 today. And then we have transferred 35 technologies to the industry. So this is Amity. And then we have Amity Innovation Incubator, which has nurtured more than 1,200 startups in our, we have Amity Venture Capital. So this is what is Amity Research. So this NMR facility, which is being added, will bring more connectivity, collaborations, partnership with not only institutions, but also with industry. So I wish all the best, wish you all the best, Mona Lisa, and the whole team of Amity Institute of Click Chemistry and Research Studies. The final, the carry home message, takeaway I would like to give you is, let us look at new avenues like artificial intelligence, data analytics, quantum. How do we bring in this click chemistry as well as chemistry field? Because then you can synthesize molecules very fast. You can predict the greenness, the impurities, byproducts, everything can be seen so carefully. So look at application of emerging technologies like AI and quantum in chemistry. This is one message. The last message is India is now becoming a Viksit Bharat, a developed India. That is the vision of Honorable Prime Minister to our country. And each institution like Amity, IIT, ISER, everyone is contributing towards this growth of India as a developed nation. So we must all think that our role is just not only to do our research, innovation, publish papers, file patents, develop products or technology or processes, but to contribute to nation building. So I'm sure whatever you do, it will lead to inclusive growth and sustainable development, which will see also Atmanirbhar Bharat, which will be self-sufficient in technologies, chemical process technology, chemical engineering technology. So all this is the final message I like to give. I wish you all the best for these deliberations and my blessings to all of you. Thank you.
Thank you so much, sir, for your kind presence, your blessings, and motivating us as always. May I now humbly invite on stage Professor Mona Lisa Mukherjee, Director AICCRS, to welcome our guest and present her opening remarks. Please put your hands together to welcome her. I request all our esteemed guests to please be seated there on that side of the dais so that they can have a better understanding of what AICCRS is.
A very good morning to one and all present here. Thank you for joining us for the one day international symposium on Bioinorganic Chemistry 2025. It is my proud privilege to warmly welcome our visionary Honorable Founder President Sir, who might be joining online, Dr. Ashok K. Chauhan, Honorable Chancellor Dr. Atul Chauhan, Honorable Vice Chancellor Dr. Balvinder Shukla, Professor Selvamurthy sir, and all distinguished emittents and esteemed guests and participants. This symposium has become reality due to their constant guidance, encouragement, and unwavering support. Now, to reach new destinations, new avenues are paved. With the blessings and vision of our Honorable Founder President Sir, the Amity Institute of Click Chemistry Research and Studies came into beginning. The journey began in June 2011 when I served as an Indian Distinguished Visiting Fellow at the University of Nottingham, United Kingdom, which was bestowed on me by Royal Society of Chemistry. Given to my interest, I chose to work with John Moses, Associate Professor at the School of Chemistry in the exciting area of biomimetic diversity-oriented synthesis. It was during this period that I initiated research using a few click reactions, a field of immense importance in drug discovery and development. With a vision to establish a center of excellence of biomimetic research at Amity University, Dr. Moses and I focused on developing collaborative projects. I also shared the emerging significance of click chemistry with the scientists at Amity University, highlighting its growth relevance in organic synthesis. To further strengthen this collaboration, John Moses visited Amity University in January 2012, where he was honored with the title of Honorary Professor at Amity Institute of Nanotechnology, Chair Professor for Natural Products at Biomimetic Chemistry at Amity Institute of Biotechnology. I would like to say that I started my career with Amity Institute of Biotechnology after completing my PhD for Center for Biomedical Engineering, followed by a postdoctoral as a CSIR RA from IIT Delhi. So they have the opportunity to get the honorary positions in biotechnology and nanotechnology, because nanotechnology, where our collated team members to come up and join hands with us to do some research in the area of nanobioconjugates. So this foundation ultimately led to the establishment of AICCRS under the aegis of Amity University in January 2017. AICCRS stands today as a testament to the visionary leadership of our Honorable Founder President, sir. This institute is dedicated to exploring innovative molecular scale technologies with potential for profound societal impact in energy, healthcare, environment, and sustainability. AICCRS actively collaborates with all the Amity campuses across India and globe, as well as with the leading research establishments and organizations nationally and internationally. In the realm of chemistry, the possibilities are endless. Every molecule can be made, but the challenge is to design to the proper 3D structure and come out with some biological applications or applications in the area of energy, healthcare, and other sectors. So having that in mind, we started Amity Institute of Click Chemistry Research and Studies, where we first pioneered the masters in molecular chemistry to design materials in molecular scale. So having said that, let me showcase a few slides pertaining to Amity Institute of Click Chemistry Research and Studies. These slides highlights our journey, achievements, ongoing research initiatives, and the collaborative ecosystem that continues to drive the innovation at AICCRS. So as you see, John Moses from Nottingham University, we got the opportunity to also meet other scientists from IIT Madras, Dr. Samad, who also received the Distinguished Fellowship, Dr. Ujjwal from IIT Bombay, and several others who have received the Distinguished Fellowship at that time in 2011. Followed by that, John was invited and we bestowed on them the honorary professor. And as I was an associate professor at that time in biotechnology, so our director, Professor Srivastav sir, late Professor Srivastav sir, is there along with Professor Ashok Chauhan to bestow on him the honorary position. So visit to Nottingham University with Mr. Ian Jones and other distinguished fellows as international office with Professor John Wood, Mr. Ian Jones at House of Square, Tavistock Square, London, working in the laboratory of John Moses, with research groups of John Moses, with Dr. John Moses officials at University of Nottingham, and receiving the Certificate of Indian Distinguished Fellow from Professor Sahara O'Hara at the end of 4 months, the Pro Vice Chancellor of University of Nottingham. Then John visited at Amity University, and at that time I was the single person in Amity Institute of Click Chemistry Research and Studies, but I never stopped working as a single person. I tried to collate people from Amity Institute of Biotechnology, Amity Institute of Nanotechnology. That's how Professor Bishwajit Shah, Professor Sandeep Chakravarti, Dr. Debolina Rai, Dr. Jasleen Kaur, and others, Dr. Koel Shinad, they all started working with us. So now, in 2019, slowly, people started joining Amity Institute of Click Chemistry Research and Studies. And it was a very nice moment in 2017, launching the Click Chemistry Research Program. And it was Brian Smith from University of La Trobe, Melbourne, to come and initiate the process. So Click Chemistry, before going into the details, let me introduce, because we have started in 2017, and it was a big challenge to make people understand that this can be an institute, because people used to think that, oh, click chemistry is a tool for doing STM research. But see the visionary approach of our founder president, sir. We never thought of that. In 2022, click chemistry got the Nobel Prize, and the person who got Nobel Prize in Sharpless, in epoxidation reaction, Professor Barry Sharpless again received the Nobel Prize in 2022. However, this Nobel Prize was shared between three people: Caroline Bartholdi, Morton Mandel, and Barry Sharpless. Caroline Bartholdi took the click chemistry inside the cells and have done the click chemistry without disturbing the mechanism of the cells. So this is the beauty of click chemistry, that it is not only having implication in material science, in the sectors of energy, environment, but also to the healthcare, which is a really an important area when you talk of going to the in vivo system. So Stanford chemist Caroline Bartholdi was awarded the Nobel Prize in Chemistry for a development of bioorthogonal reaction, which allows scientists to explore cells, track biological processes without disrupting the normal chemistry of the cell. Morton Mandel, the discovery of copper ACC reactions opened upon new opportunities in research, development, especially in the area of material science, pharmaceutical development, and for his discoveries, Mendel was awarded a share of 2022 Nobel Prize. And the man who received the twice Nobel Prize, Professor Barry Sharpless, coined the concept of click chemistry, where molecular binding blocks snap together quickly and efficiently. In 2002, Sharpless and Morton Mandel, independently of each other, developed an elegant and efficient chemical reaction, the copper-catalyzed azide alkyne cycloaddition. And you will be happy to know, and it is worth mentioning, that I got the opportunity to meet Professor Barry Sharpless in John Moses' lab, and he said that you should start the Click Chemistry Institute, because there is no academic institute in the name of click chemistry. So why don't you go back to India, apprise people about the novelty of click chemistry? It doesn't mean always azide alkyne click chemistry or suffix click chemistry or any other. You can tell that metal conjugation of ligand, that is also click. So it is not that you only need to do azide alkyne, bioorthogonal, or other reactions. Click chemistry can have that momentum to bring people at the interface of chemistry and biology and do great work. So Nobel Prize for the year 2022 was given to click chemistry. Methods to collect molecules, it is essentially the same way you built Legos. It just clicks and the molecules are coupled together. Amity Institute of Click Chemistry started with John Moses as the chairman. He's right now heading as a chair professor in Cold Spring Harbor Laboratory in Long Island. And Cold Spring Harbor Laboratory is ranked #1 by Nature because most of the Nobel laureates are working there. So John has been awarded as a chair professor recently from Cold Spring Harbor Laboratory. So I would like to show this because always John wants to show this, how the reaction is done, and you will see the Nobel laureate coming and doing the reaction, putting the magic catalyst to get out the product out of that is the suffix-derived polymer.
One coupling partner, then goes the other, but nothing's going to happen yet. Need to add some solvent. What are we using, Josh?
DMF
Is
dimethyl formamide.
monomers are pretty soluble, but just to help them on the way, we're going to heat it up a little bit just to get them nice and soluble. So now we're going to let it stir a little bit, maybe cool down a little bit, just to take the edge off it. And then Professor Sharpless is going to come along and add the magic catalyst. The catalyst.
You see Professor Sharpless coming forward to add the magic catalyst.
We have a lab, particular catalyst.
Yes.
So it's a proud moment for us. There you go. Are we ready? Go. But you can't really see what's happening. So that's at the level you don't really see anything. Go. as it proceeds, the polymer becomes more insoluble as the molecule gets longer, it becomes less soluble. And eventually we'll start to see some material crashing out of solution. Let's see what happens now. Hopefully the material should crash out. You can see little like fibers appear right in the solution. Yeah, squiggly. I don't know. It looks unstable.
So this is the polymer made with Sufex click chemistry. And I would like to tell you that in 2022, for the first time, Amity Institute of Click Chemistry Research and Studies received a grant in Sufex click chemistry from Department of Science and Technology, and a big round of applause because it is a very new research field. Sufex click chemistry, people knows about azide alkyne, people knows about bioorthogonal, but we have come up with Sufex click chemistry, and we are taking that to the nanomaterials, conjugating the carbon quantum dots and graphene quantum dots to make a Sufex ligand, and then go for the biological applications, especially in the cancer theragnostics. So AICCRS team research areas, as I said, that I am the leader as Professor Mona Lisa Mukherjee, and we all work in a very cohesive manner. It is, although I am a director, but I try to maintain a very cohesive relationship so that all the faculties can come together, feel that environment very homely, and work in the research labs, take classes, meet faculties, have brainstorming sessions. So Saikat Datta, his research area is functional nanomaterials for electrochemical charge storage application, energy bioscience, fuel and nanomaterials for micronutrient sensor and delivery, biomaterials for therapeutic application. Professor Sandeep Chakravarti, wastewater treatment, photothermal desalination of water, synthesis of novel materials for diverse applications. Dr. Ranjan Patra, the second man of AICCRS, bioinorganic modeling of heme, non-heme metallozymes, supramolecular hydrogen and halogen bonded network, DFT calculations of mechanistic investigation for enzymatic model. Dr. Vivek Mishra, who has started the first click chemistry, and you will be happy to know, will show you that last year he has received as a corresponding author chemical review in the area of click chemistry, which is a very big contribution for Amity Institute of Click Chemistry Research and Studies. So his area is click chemistry, coupling reactions, bio-waste to valuable products, green chemistry, ionic liquids. Dr. Pooja Prasad, who has joined as assistant professor grade 3 and works in the area of drug delivery, medicinal chemistry, antibacterial agents, anti-cancer agents, pro-drug activation. Dr. Milan Bera, it's my proud privilege and honor that Dr. Milan Bera has joined. He's from Dr. Debobroto Maiti's group, and he has literally started that organic hub in Amity Institute of Click Chemistry, an entire Amity universe, which was lacking till date. So thank you, Dr. Milan Bera, and I hope you will be coming up with very good publications. You have already started with good work. So he works in the area of energy transfer, photocatalysis, photoredox catalysis, remote CH activation, asymmetric catalysis, drug discovery and process. Dr. Debobroto De has recently joined with us, Ramalinga Swami Fellow, an important member, because me and Dr. Pooja were feeling very lonely that we are only working with the biological molecules. So a person who has come, who understands biology, a chemist converted to biologist. So he works in the area of cellular biophysics, cell biology, protein biology, biochemistry, drug off targets identification, confocal and super resolution microscopy. And you may be happy to know that he has developed methods in confocal while he stay as a staff scientist in Weizmann Institute. And now he is going to do that in Amity University under the affiliation of Amity Institute of Click Chemistry Research and Studies. 2 new members are joining in January 2026. That is Dr. Biplab Manna, who has received DHR ICMR fellowship with us. Dr. Avinash Dhamija, again a student of Professor Rath, who has received Ramanujan fellowship. So these are the areas where I am working: carbon nanohybrid, hydrogen nanocomposites, molecular science and research. and I've been honored to act as an associate editor in chemical biology and chemistry of scientific report Nature, biocatalysis, and biotransformation. My area of work is pertaining to material biology, click chemistry, molecular science, algal nanobionics, drug delivery, biosensing, and bioimaging. I already spoke about Saikat Datta. He's the top 2% scientist ranked by Stanford University. His area is material chemistry, nanoscale science, electron absorptions, electrosorptions, supercapacitor, metal ion battery, biosensing, nutrient delivery in crops. Professor Sandeep Chakravarti, from whom I learned actually the nanomaterial chemistry, because my expertise was in porphyrin and metalloporphyrin mimicking of cytochrome P450 and nitric oxide synthesis. But when I joined Amity University, I got the first project in the area of porphyrins and metalloporphyrins, conjugating them with the carbon nanomaterials or other nanomaterials covalently and non-covalently. And all this nanomaterials concept I learned from Professor Sandeep Chakravarti, who is a student of Professor C.N.R. Rao, the great C.N.R. Rao, and Professor Natarajan. His area of work is solar-driven desalination, wastewater treatment, carbon dioxide sequestration, metal organic framework, and carbon-based nanomaterials. Ranjan Patra started his career as a DST-inspired fellow, and after completion of his DST-inspired fellowship, he was taken in Amity's payroll as an associate professor. He did excellent work and published ACS catalysis, crystal growth and engineering design papers, ACS crystallographic papers. His area pertains to supramolecular chemistry, bioinorganic chemistry, single molecule magnet, photoluminescence, catalysis, and computational modeling. Dr. Vivek Mishra has joined us in 2020. He works in the area of environmental remediation, green chemistry, hydrogels and drug delivery, click chemistry and heterocyclic analogs, ionic liquids, aerosols, and functionalized carbon quantum dots. Dr. Pooja Prasad has joined in 2022, and you will be happy to know that after joining, she got 2 projects within a year. That is CSIR Aspire, which is a very prestigious project for women scientists given by CSIR, and the DST Startup Grant within 1 year of joining, and published several ChemCom papers and feature articles in ChemCom after her joining. Her work pertains to the area of drug delivery, medicinal chemistry, antibacterial agent, anti-cancer, and product activation. Dr. Milan Bera, as I told, that he has started the Organic Chemistry Hub first time in Amity Institute of Click Chemistry and in Amity Universe. We had organic chemist, but what Dr. Milan Bera is doing, publishing organic letters, JOC, and green chemistry, and I'm hopeful that in the coming future, he will be also publishing in JAX from Amity Institute of Click Chemistry Research and Studies. So he works in the area of energy transfer photocatalysis, photoredox catalysis, ligand-tuned metal catalyzed CC bond, remote CH activation asymmetric catalysis. Dr. Debobrata De developed the confocal-based fast microscopic methods to detect molecular motion inside the live cell. And you'll be happy to know that one of his work, Drug Inside the Cells, A Bit of Light, has been highlighted as the top article, hot article in Science. And he worked as a foreign expert, science in Israel, and he has joined with us as a Ramalinga Swami Fellow. These are the glimpse of our granted patents. We have applied from Amity Institute of Click Chemistry Research and Studies around 30 patents, and these patents are granted. 3 are more towards technology transfer, which I'm not showing right now. 2 Angventa Chemi from AICCRS, back-to-back 2024 and 2025 from Dr. Ranjan Patra's group and Dr. Saikat Datta. It's a very proud privilege and honor that from Amity Institute of Click Chemistry Research and Studies in the entire Amity universe, this kind of publications has come, which is showing that the eminence and the work, and it is really a testament of hard work they have done inside Amity University under the affiliation of Amity Institute of Click Chemistry Research and Studies. My group has also published in ACS Nano and it became the hot article. You will be happy to know that student is now working with Ali Khadim Hussain, who is a top-notch biomedical leader from Terasaki Institute. He's also a professor cross-appointed with Harvard and MIT in USA. So Dr. Adiba Shakil is working and she has received the first author paper in ACS Nano, and I have worked that in Amity Institute of Click Chemistry Research and Studies, Material Horizon, also in the area of diabetic wound healing, green chemistry in the area of bioimaging of cancerous cells, especially the HepG2 cells and pancreatic cells. Nano today in the area of coronavirus, how carbon quantum dots and click chemistry can conjugate together to combat the coronavirus. That was the News and Views article featured as the hot article by Nano today. Chemical review, as I told you, Dr. Vivek Mishra and Dr. Han Juelov, both of them as joint corresponding author, has received this chemical review in 2024. Biomacromolecules received by our student, Dr. Ms. Radhika Chaurasia and Ms. Bani as one of the Editor Choice Award to work with carbon materials and hydrogen nanocomposites and taking it towards stem cells, proliferation, growth, and differentiation to a particular lineage, that is adipocytes, osteocytes, or chondrocytes. And we are also taking that to the neuronal cells. Yes, that learning of stem cells was handheld by Dr. Sujata Mohanty, who has established the Special Center for Stem Cells in AIIMS, and we got the opportunity to guide a student, and my 8th student, Misbah Masood, after completion of her PhD, got the postdoctoral position from 3 places, that is Oklahoma, Michigan, Ann Arbor, and Johns Hopkins, and now she's working with organ and organoids in Johns Hopkins. So Misbah, she has done this work in Asia's Applied Materials and Interface, chemical engineering work, which has come as a hot article by Professor Sandeep Chakravarti, me, and Dr. Geethika Jain in harnessing the cotton fabrics for, along with ZIF, that is the Metal Organic Framework for Sustainable Photothermal Desalination. These are the research publications in click chemistry in last 5 years. We had a very hardworking scientist, Namit Haran, who has published 2 organic letters just after his joining. He's now working with Abu Dhabi University as a distinguished scientist. These are some of the organic and inorganic chemistry publication in last 5 years, organic and inorganic chemistry publications in last 5 years, material chemistry publications in last 5 years. We also work in the area of sustainable chemistry with algal nanobionics, where carbon nanomaterials with different functionalities, that is having graphitic nitrogen, pyridine, and pyrrolic, helps to give the biofuel and the mass, and from there an important product, that is lutein, comes for, which is very important product for eye. Material chemistry publication in the last 5 years, pharmacological publications, biological, and these are the laboratories established by us. Biological and Molecular Science Research Laboratory, Electrochemical Sensor Laboratory, Materiobiology, Advanced Nanomaterials Laboratory, Animal Cell Culture Laboratory, Photocatalysis, Synthetic Methodology, Molecular Energy and Catalysis, Molecular Materials Research Laboratory. We have received 15 crore grant with 7 years establishment of our department from these funding agencies. We offer 2 programs, Masters in Molecular Chemistry and PhD in Molecular Science and Engineering. In Amity University, modernity blends with tradition. That's why we have unique addition to learning with foreign language, communication skills, behavioral science, human values, and that's how we try to brainstorm the students. Achievements of EICCR students, Rohan Bhattacharya is right now working with Harvard Medical School. He has the opportunity to work with us as an intern student. Dr. Misbah Masood was my 8th student. Dr. Akanksha Agarwal was my 7th student. She's working right now in School of Medicine. Piyush Garg was our intern student, just recently graduated from University of Waterloo, Canada. Abhayvarti Selvam, he's working in UC Berkeley. He just came yesterday to meet us. He has done very good work and now working with Rebecca Abergel in the area of radiophysics. Sampath Jivananand, he's working in Korea. He has also worked as an intern student. Dakshi Kocher worked as an intern student, got 100% scholarship at Carnegie Mellon University, USA. Adiba Shakil, as I said, she was in Abu Dhabi and now she has joined Terasaka Institute. Dr. Aarti Singh, Dr. Deepa Suhag, Mr. Arnav Chakravarti did masters with us and working with 100% scholarship, University of Miami. Dr. Rahul Patel did very good work in the area of nano energy. He has published several top-notch journals like Chemical Engineering, Small, Energy Environmental Science under the mentorship of Dr. Saikat Datta. Simran Jindal, our student, master degree student, doing great work in Israel, who has worked under the mentorship of Dr. Vivek Mishra for 1 year and also under my mentorship for 1 year. These are the students, Mr. Om Narayan and Mr. Shivam, who got the opportunity to work as a visiting research scholar in the Chemistry of Environmental Science and Department. And this year, in 2025, they got JMC Pate in the area of sodium-ion battery to make the solids electrolyte. And me and Dr. Ranjan Patra did this collaboration with Dr. Vitadello of City University of New York. And now, a great news, Dr. Rafia Siddiqui received the Newton's Fellowship from Amity Institute of Click Chemistry Research and Studies, which is a top-notch fellowship, and it is very prestigious, very competitive. 4 or 5 students from India normally gets this kind of fellowship per year, and Rafia Siddiqui got this fellowship, who has done work under the mentorship of Dr. Ranjan Patra and published Angwin Takemi and Coordination Chemistry Review. So a big round of applause. She's now working in the University of Bristol. Some of the achievements, it is my honor that I got an award, prestigious Padma Vibhushan Dr. A.R. Kidwai Memorial Oration Award for outstanding contribution in science and technology from the great Professor J.P. Talwar, who is known for Talwar innovation. He's the one of the scientists who was nominated for Nobel Prize from India, although he did not get it. But nomination is also a big thing. So it was my honor to get it and working in this area of nano science and nanobiotechnology, nano click chemistry related area. I was invited by Delhi University and I got that recognition. Some as C in woman chemistry, as woman in chemistry, fellow of Royal Society of Chemistry, and Telangana University in 2024 has bestowed on me honorary professor from Dichipalli and Biknoor campus. This is also a short recognition for me inside Amity Institute of Click Chemistry, that state government universities also recognize the hard work. I have been offered a visiting scientist position. Again, I am flying next year to Boston and will be meeting University of Lowell, where I got the opportunity to give a keynote speaker as a keynote speaker in the area of polymer and how I developed, how graphene quantum dot helped to direct the polymeric self-assembly to Kagom and Janus, and they transferred their payloads, that is 5-fluorouracil, to the targeted site, that is the colon, and preventing the colon cancer. So that, because of that work, they gave me the recognition that I can be visiting them every alternate years and can give some lectures in their department, University of Lowell, Massachusetts, and talk to their students. And in that, I got connected to Professor Anthony Giuseppe, who is right now conducting a great Congress in 2026, that is the Biomaterial and Bioengineering Congress. I give this statement to you very humbly that I have been nominated as an international organizing committee member along with Samir Mittagrotri of Howard, and we will be able to see Jennifer Doudna there in that meeting, and I will be working as a keynote speaker and session chair. So this is the team. I was invited from IIT Delhi. My guide was from IIT Delhi Center for Biomedical Engineering. He said that, Mona, you should come because Morton Mendel will be visiting. And always I try to take my team together, because without a team, you cannot do a good work. So entire team in IIT Delhi and meeting Professor Morton Peter Mendel, who has received the Nobel Prize for Click Chemistry. We have the honor to meet Professor Ashutosh Sharma, who has tweeted as well as provided some of the good statement about our institute, that this is the place where science and engineering will foster, because I have seen the hard work, the patience, perseverance, and passion among the scientists and the self-motivated students, that how they are coming up with good research papers and patents. So this is, we are Click Chemistry Award of Excellence. Amity has received from Ministry of Commerce, which already Dr. Selvamurthy sir has mentioned, that we got the commercialization of patent from Ministry of Commerce 2020, because we have filed and we got commercialized of our patents. That is the National Intellectual Property Award 2020. Amity University has been conferred upon CII Industrial Intellectual Property Award 2024. I'm not going to the details. And today's day, DST FIST project, which is around 3.2 crore, but DST has given us 2.35. Along with that, our founder president has given us the remaining amount to come up with the state-of-art DST FIST project, the 400 megahertz NMR facility, the state-of-art facility. The AICCRS team has done it. So it is not only the AICCRS team, there are other collated team members. I must acknowledge Professor Bishwajit Shah, Dr. Debolina, Dr. Jasleen, Dr. Seema Bhatnagar, who came together, handhold us, and we took the opportunity to give our presentation in DST Feast and grab that award and come up with that award and start that facility under the definition of Amity Institute of Click Chemistry Research and Studies. And we will be not only helping the Amity universities, we will be helping some of the Delhi NCR universities who are deprived of this kind of instruments. We will be giving them in cheap rate. And this is the thing we are going to help the mankind so that they can come with research excellence as national. So this is the weekly demand of NMR samples at AICCRS even before the inauguration. Week 1, 2, 3, 4, 5. These are the samples we are getting every week. And we are coming up with workshop from 24th November, and it will be done every month. We will be giving hand-on training on NMR instruments and data analysis, insights into advanced NMR techniques and applications, interactions with experts and researchers in the field, skill enhancement for research and industry, certificate of participation for professional value. Over 60 participants have already registered for NMR workshop. Joint researchers, especially the PhD students who have come from Delhi NCR, I think 6 of them have come with for this conference. I would like to say joint researchers and industry professionals from across the country, secure your seat now. And now the mantra of Amity Institute of Click Chemistry Research and Studies. This is a collective mantra of all the faculties of Amity Institute of Click Chemistry Research and Studies. Innovation, top-down product-oriented approach is the key. Work on a platform development where you can write papers, perfect it before thinking on a product, protect the IP as early as possible, very important. Mature the technology in the academic environment, given the lack of the ecosystem for VC funding, the technology startups. Utilize the government sources of funding for company initially less equity dilution. Professors and students can build a company. Team is important. Work towards increasing the value of equity, not fighting for equity. Involve students in the enterprise, a strong motivation for them. Look for the areas where there is a great domestic market demand, fewer controls, awareness of markets, networking is easier. 3 Ps are very important: passion, patience, and perseverance. No matter what we learn in life, the pedal keeps changing. Pedal hard and keep pedaling. Success, it is a mixed performance, mixed of all this, that is performance, persistence, discipline, attitude, failures, hard work, risk, determination, excels, and patience. Thank you so much. Thank you for patiently hearing me, and I'll be happy to have any questions, any suggestions, so that we can upgrade the institute and take it to a long height.
Thank you, ma'am, for providing glorious insights about AICCRS. Your passion and perseverance is truly evident from the remarkable success stories of your institute. Many congratulations on that. Moving on, life is chemistry with metals, as said by Richard J.P. Williams, who is the pioneer of bioinorganic chemistry. This quote beautifully captures the essence of the field, emphasizing how metal ions are integral to the chemistry of life itself. Bioinorganic chemistry lies at the dynamic interface of biology and inorganic chemistry, exploring the essential roles that metal ions and inorganic cofactors play in biological systems. This multidisciplinary field seeks to unravel how the structural and electronic properties of metals contribute to the complex mechanism of life, from oxygen transport and electron transfer to catalysis and gene regulation. At the molecular level, the structure of metalloproteins and metalloenzymes provides critical insights into how metal centers orchestrate biochemical transformations with remarkable specificity and efficiency. Understanding these structural motives not only deepens our comprehension of biological processes, but also inspires the design of biomimetic catalysts, metal based therapeutics, and diagnostic agents. The functional dimension of bioinorganic chemistry extends to diverse physiological and environmental contexts, including photosynthesis, nitrogen fixation, oxidative stress regulation, and metal ion homeostasis. From applications in medicine such as anti cancer and antimicrobial metallodrugs to innovations in green catalysis and bio inspired materials, bioinorganic chemistry continues to expand its relevance across scientific and technological frontiers. By bridging fundamental understanding with applied innovation, the field stands as a cornerstone of modern chemical biology, promising new solutions to challenges in energy, sustainability, and human health. In essence, bioinorganic chemistry exemplifies the seamless unity of the inorganic and biological worlds, where metal ions serve as the silent architects of life's molecular machinery. As our understanding deepens through structural, spectroscopic, and computational advances, we move closer to harnessing these natural design principles for transformative innovations in medicine, energy, and material science. The continuing exploration of metal biomolecular interactions not only enriches fundamental science, but also paves the way for sustainable and health oriented technologies that mirror the elegance of nature's own chemistry. With this brief description about bioinorganic chemistry, and in order to gain more insights about this interplay, we will now start with the pre-lunch session, which comprises of two talks. This session will be chaired by Dr. Ranjan Patra. Dr. Patra is an associate professor at AICCRS and also a PhD student of Dr. S.P. Rath. So may I invite Dr. Ranjan Patra to start the session?
Good morning. Thank you all. As a convener of this conference, I welcome you all. And we understand we all are waiting for the lectures, particularly because this is the most scientific importance for us. So, past lecture by Professor Furuta. Professor, before start his lecture, I give some little introduction. So, Professor Furuta has done PhD from Kyoto University, and then postdoc from University of Texas. And after that, he joined as a professor in Kyushu University. And particularly, if you understand that a lot of postdoc students from Professor Furuta are in India. Among them, I can able to tell Dr. Gokul from IIT Trivandrum, Iti Gupta in IIT Jodhpur, and all others. Also, our Amity University, Amity Mumbai, also one student who is postdoc fellow of Professor Furuta. And obviously, he is now the distinguished professor of Shanghai University and Bajra fellow, Bajra professor at IIT Kanpur. We are really thankful that Professor Furuta, and I also extend thanks to Professor Roth to give the opportunity that Professor Furuta is visiting India. So we are really lucky to get Professor Furuta at this today's lecture. So we are really happy to get your lecture. Thank you.
Okay. Okay. Thank you for kind introduction, and I'd like to thank the organized committee that invite me and give me a chance to talk my special topics. Um, I'm sometimes called a confused porphyrin chemist because company is not confused, but only I was very, very confused. So today, I talk about some things, peculiar chemistry that is slightly similar but slightly different from that of a regular porphyrin chemist. So I hope you will have some interest to my compound. Okay, let me start. Okay. That's the general introduction that remind you the structure of porphyrin. The porphyrin is, you can see the many color pigment of nature are like a plant, that chlorophyll, or body in the blood cell, the red color is due to the hem that, but you can once more learn that porphyrin's basic structure is 4-pyrrole, tetrapyrrole macrocycle conjugated. And nitrogen is pointing inside to form. Okay. No. Mike? Okay. 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 Then meteoroid captured by formed nitrogen. But different from that role, the meteoroid change. Okay. Then these two are highly involved of the energy conversion, like photoenergy to the chemical bond, and the, burning the carbohydrate oxide, respiration, like that. So due to that versatile property, the porphyrin is called pigment of life. And but at the same time, because of the lot of functional, it can be used for like photodynamic therapy or sensing and something like that. But my compound, which I dare to say my compound, is like this. One of the pillow is inverted. So due to that, nitrogen is going outside and carbon inside. So that makes some perturbation electron property and especially that form the carbon metal bond. So organometallic compound and nitrogen outside. That means it's like a pyridine or pyrrole of expanding. So to regularly 6-pi system change to the 18-pi system. So that is very interesting because we can tune that acidity or basicity or metal coordination, something like that, catalyst. That is the motivation we are doing this compound research. And there are many ways to modify the porphyrin. The basic porphyrin chemistry is usually peripheral modification, substitution, fusion, something like that. But uh, other approach is core modification. So just replace one of the pyrrolene to other aromatics, like a benzene or sulfane, fluorine, something like that. And confused porphyrin is just changing the linkage, even using pyrrole. Or uh, deco- deconstruct the porphyrin framework. So both are core modified porphyrin. And as I said, porphyrin, confused porphyrin is isomer of porphyrin, the same molecular weight and molecular structure, molecular formula. But at the same time, it's carboporphyrin. So we are very interested to work on. And the compound was found almost 30 years ago by us, and independently as Professor Latos Grazinski in Poland, Wrocław University. So I would just want to tell that the beginning of this finding by us and also Latos Grazinski. I was in Texas as he introduced, and just started, Professor Just Sessler started expanded porphyrin chemistry and find out the property. He found the sapling. So one additional pyrrole incorporated in this macrocycle. Then the core bigger. Then instead of metal, uh, an ion, bigger size anion captured. This is a fluoride. But if we put the chloride, change the fluoride to chloride, then the size is too large, so it cannot fit it. So after finishing that postdoc work, and I started my independent work, returning to Japan, Oita University, I tried to make that expanded porphyrin more selectivity using anion template synthesis. And instead of beta alkyl type, I like to more simple meso allyl type. That is easy, at least for me at that time. So just pyrrole and benzaldehyde and add some anion. Then I can get some maybe like a pentaphyrin like that. And Latos-Grazinski want to make a mesoallyl sapling like that. So he changed the 1-to-1 ratio, more pyrrole. And both are not get this. And later on, he gets very small amount. But what we get is as a regular morphine as a major product, but byproduct, even 5-7% smaller, but we can clearly get another compound which was characterized by X-ray and other spectroscopy, and it was found that it is tetrapyrrole conjugated porphyrin, but one of pyrrole is inverted. And you can see from X-ray side view that is quite different from regular porphyrin. It's completely planar because of in the hydrogen bonding. So that is due to 3 hydrogen inside 4. It's state repulsion make that pyrrole tilted. But later on, that famous synthetic porphyrin chemist, Lindsay group, has shown that just changing the regular synthetic porphyrin BF3 TFA to methanesulfonic acid, then the chemical is completely changed from regular porphyrin. Usually they don't find any confused porphyrin, but now methanesulfonic dramatically increase. So after their paper, many other groups started this kind of jump into this area for metal coordination. since then, we have worked on very lot of work and aromaticity, tautomerism, absorption, something like that. But today, I just because of time, I focus on more near infrared eye using starting from this in confused popping. And this is just to show you how and confused popping form a group. So the regular popping is just a two. It is including tautomers. But singly confused one, doubly confused one, triply confused, tetra confused, so depend on the nitrogen position, so many structures of all. So we can get, just changing the linkage, we can get a very diverse porphyrin family like that. That is interesting. One is just, if we start a doubly confused porphyrin, uh, structure is a pi stacking like that. But once metal, kappa metal inserted, it's form a kappa 3 complex. Then one of the pyrrole is immunotype, like a pyridine-like basic, but one is pyrrole, NH, acidic. So the crystal structure shows a hydrogen network, one-dimensional polymer like that. And so conceptually, and confused porphyrin, as I said, it's a expanded pyridine, pyrrole, and imidazole in the other case. But still, we are trying to make the triply tetra confused system. And the very, very fundamental one, aromaticity is preserved in this structure. You can see that regular porphyrin, because of the link current shielding, so in NH and outer CH, that the difference chemical shift shows that strength of aromatic strength. But in confused porphyrin, due to the break of symmetry, so many signal each appeared, but still in NH and outer CH, the same. That means aromatic magnitude is similar. But more interesting one is that tautomerism. So if you dissolve the compound, it's a red color. The porphyrin like Sole and Cuban appear. But if we change the solvent to like acetone, pyridine, dimer, then color change green. What that occurring is that the in one of the eight proton is migrate to the outside. So now it's a in a 3H type to in a 2H type. That is slightly conjugation break because of the cross conjugation. Less aromatic, but still aromatic. So you can see that. That is quite interesting for metal coordination. And such tautomers can be easily induced, not only solvent, but adding an ion. So it fixes it, then hydrogen bonding, stabilize this form, and the binding constant is larger. But once fixed this, attaching the divalent metal, the binding constant is 10 to the Hz. Just one hydrogen bonding is too amazing. So we think that the anion pi interaction is included to this system. Since then, many people, and including us, trying to catch up with porphyrin chemistry. That means coordination chemistry of periodic table of porphyrin, periodic table of and confused porphyrin, but still behind. And even though color lights, but very few papers, just one or two, we did make the compound and structure characterization property like that. So metal coordination is one of the topics highlight of in confused porphyrin. So due to the two tautomic form, it can bind divalent metal like palladium, or even trivalent metal like a silver or gold, something like that. But even though that kappa, usually kappa 2, the paramagnetic, but once oxidized, it gave kappa 3. Only difference is whether hydrogen is attached or not. And the structure shows smaller ion size of copper. Bond length is smaller like that. But it's stable. we can isolate by column and diversely change. And taking advantage of organometallics in the carbo is more reactive. So we can just add the Higgs nitrogen coordination ligand, pyridine ligand. Then the compound catalytic activity, right, like a cyclopropionation of styrene, largely increase. They, in the certain condition, they, regular porphyrin catalyzed but very small. Confused porphyrin much better, but once Higgs nitrogen attached, much larger. So not so many people working on and both for the catalytic use, but I think in some reaction must be very applicable to that with this compound. Now I'd like to talk about some near-infrared dye chemistry because it is one of the highlight of recent people. NIR dyes are expected, especially for the biological sensing or therapy or like, because usually green light or something is not penetrate, but the red light is more, we can see red color. So that light scattering and autofluorescence are much less in the near infrared region, especially more than 1,000 nanometer. We call the NIR 2 or 3 or something like that. And NIR dyes, several dyes people making, but still needs the stability and biocompatibility or something like that. So we are interested of this area because even the freebase and confused porphyrin is already 720 30 nanometer absorption. But the interesting one is that pyrrole easily rotate invert. This is one example. So because of the inner outer coordination, like Logium 1, but it heated like iridium. Then the pyrrole inverted and bleached. So this pyrrole is much easier flip rotate. And this can be done by just bromination, room temperature, brominated this alpha position. Then inverted and fusion occurred. Then absorption band likely shifted to longer waves over 1,000 nanometer and emission we can observe. And this can be reversibly returned to this and confused by the ring opening by attachment of attack of nuclear fire. This can be used for the anion sensing in biological system because porphyrin is even confused porphyrin is more emissive than this infused porphyrin. So by in some water solubilized pH by attaching that water soluble group, then checking cysteine, homocysteine, glutathione, then much faster and efficient conversion, detection of cytokine. So must be usable for biosensing in the cell also. Okay, but we just interested what happened double fuse because we have a double confused system. Then calculation shows that porphyrin, infused porphyrin is just like a 22 pi system. But double confused system might be 30, this one, 2 system, like a pi system. So we try. This is a little bit stepwise, but we found that this double confused system show that once 1,300 nanometer in the longest one. That is corresponding to 42 pi system. So even tetrapyrrole, small, it just folding inside, then homolumal band gap dramatically decrease. This is one of the way to approach the near infrared dye. But another approach we are doing is that reduce the symmetry by cutting or removing one of the measuring position. Then, but we are still sticking, trying to stick to the confused system so that compound linked to the metal is carbon. Then we can get several. Very interesting one is that any linked color isomer, but also this we call bilateral. Bilan is a tetrapyro link and double bond 3 bilateral stuff. Because porphyrin is usually homolumo is degenerated, so that is due to the break of symmetry, homo is up, lumo is down, so we might get a smaller band gap compound. And yeah, that's right. Then we made it, that's it. In this case, I show you palladium platinum, but because it is quite typical and stable. Of course, we have a excess structure to prove the structure is compound is formed. But you can see that how that absorption spectrum change from free base type 683. But if we put one palladium 5949, platinum 1057, and ring closing actually boron link, so blue line 129, and palladium case, platinum case is that 1135 like that. So you can see that homo level is splitted and lumo level also splitted. So that is good. And compound is very stable. So we can use as a photothermal conversion, typically easily irradiated the temperature of solution up and turn off, very stable. And then we can see that the temperature increase by monitoring this system. And it's very, very high conversion efficiency was observed. Okay. So smaller molecule is slightly probably better for the application. And even for the logical, like this is a rhodium and rhodium base cap, it's a logical species, can be used at photoacoustic spectrum. Photoacoustic is just irradiated light is heat, changes the heat. Heat is expanded the surrounding solvent. Then we can hear that like that. So this is absorption spectrum. Then we just laser using this. Then we can hear the sound similarly. So it is very nice to use. Even this is a logical, very stable logical. Okay. But regular approach to make the porphyrin molecule to the near infrared compound is expand. We found, I was in Kyoto University with Professor Oscar. We together published a paper that is just one pot synthesis by changing the benzaldehyde to pentafluorobenzyaldehyde. Then we can get porphyrin, pentaphyrin, hexaphyrin, heptaphyrin, octaphyrin, nonaphyrin, and and the absorption spectrum shifted longer wavelength and Q band also. And the color slightly changed. And it's tedious, but still clearly we can separate by color chromatography. Because of the color is attractive, so we want to recover it. So now many paper appears from Oscar group after I left to Kyushu. But anyway, but we are confused chemistry are more should advance. We are thinking So I'm thinking confused porphyrin is N and C core. But if we add one confused ring in the hexaphenate system, we can still keep that N and C core and then C core. Then we might get that bis metal complex, sometime bis heterometal system. That might be interesting because porphyrin, the color usually property is pi-pi transition as the metal involved, metal CT, that, like that. But if we use the expanded porphyrin with two beta metal, HOMO is up and some LUMO down, and interaction metal MLCT type, if two different, so many interactions, it might be show that interesting property of this metal complex. So the simple calculation shows that if you put the palladium in the regular porphyrin hexaphenate, still the HOMO LUMO is degenerated, even though it shifted 1,000 nanometer. But if we put confused, then HOMO LUMO is degenerate broke. That means HOMO LUMO but shorter. And the palladium confused system is more. So it's one of the challenge to make this. We did it. Here, palladium, even the color, ionic size is too small still. So it's, the complex is not planar, but still we can see the porphyrin-like spectrum. And interesting absorption is around Q band is 1400. And you can see also emission. If we change to the platinum, then more shifted, like a 1700, like that. It is might be easy to make this camp. Slightly metallation is needs some technique, but we can get it. But usually hexafluorine alpha position of confused porphyrin is more electron rich, easy to oxidize. So it's G oxotype is formed, but still it's okay. Oxygen is a nice metal coordination atom element. So like this compound capture almost all metal, and some of them emissive. In the zinc case, it shows that 1,000 for emission, and in in solution in water, we can see the zinc compound, zinc sensor. As the fluorescence sensing is possible with this molecule. But this metal complex is more interesting because if we put palladium and I think it's platinum, sorry. Yeah, platinum, then the color changes to mostly black. So the black dye is formed, all the visible region absorbed. And if we change, I think one more, yeah, like that. Like a gold and palladium. So this is case +3 +2. And previous one is +2 +2. And the different method. Then again, photothermal stability is much, much higher. And stability, if we use a regular near-infrared dye, like IPG, irradiation decompose rapidly. But hexafluorine system, due to the metal stabilized, it can stable. Okay, so I have working on the actual organic chemist and step into inorganic. So first, we like to make a ligand, then examine that. So making a variety of confused one. So if you see my paper, mostly structure, one of the pillar or two highlighted in a different color. That is a confused system. So my chemistry is quite simple. We call confusion approach. Just changing the below. Indian people, Indian researchers, some of the profit like to change the below to the sulfame, furan, xeran. So hetero proofing system is more popular, but I still stick to the standard below. Then alpha to alpha beta, we can get a very diverse molecular isomer pool. Then that diversity drive us to explore the some of the good function. So like selection. So we call that one of the directional evolution for hopefully to get a more useful molecule. Okay. Sorry. So that is, I use this slide for my retirement to Kyushu University. I'm now emeritus professor, and so many people work on and collaborator. But the yellow color is Indian postdoc and student, and they help lot to develop that in computer profiling chemists. They're like that. I think I thanks to this their hard work and contribution. Thank you for your kind interest. Yes. Hmm? Postdoc. Postdoc. JSPS postdoc. Yeah, I know. I did it this February. Okay.
Yeah, excellent. Nice.
Okay. Okay. Okay.
So one question is that you showed that for when you metallated the porphyrins,
Yes.
like iridium, rhodium,
Yes.
you got sometimes mixture of two cases.
Yes.
Where the four porphyrins are coordinated into one metal and some
Yes.
are mixer, right?
Yes, yes.
It flipped.
Yes. Yes.
So how do you separate and purify, and how do you know what is the ratio of that to compound?
Oh, I basically organic chemist, as I said. I don't like to work on the grow box, something. I mostly collect the very stable compound. That means
Ah.
always chromatography. And the color is different, quite easily catch.
I think it is.
Yeah, slightly change, then correct. Dark, then throw away, something
Okay.
like that.
And the next one, towards the last slides, you showed the mixed metal like gold, palladium, platinum.
Yes.
Yeah, like gold. Okay,
Yeah.
this is a very nice system for mixed metal. Have you
Yes.
used it for any type of catalysis like cooperative catalysis, bimetallic catalysis?
Oh, catalyst.
I want
Actually,
catalysis
that electric hydrogen evolution that um, uh, actually the researcher asked me to provide me the compound. So I said, and they show something, but I could not get a clear result yet. But anyway, this hexafilin system, let's say, not much examined. Yeah, but
It's a very nice system to
yeah.
create a very new multimetallic or
True. Definitely. So we are expecting like a cyclopropylation reaction. This cyclopropylation because
Yeah.
it's rhodium, something like that. Cobalt also.
Thank you. Thank
Yeah.
you.
Very nice and impressive talk. Professor, I have one very basic question
Yes.
that porphyrins
Yes.
inside our body, they have myriad roles to play, such as porphyrins, cytochrome P450,
Oh.
right? Porphyrins, nitric oxide synthase. Cytochrome P50, 450 do
Yeah.
xenobiotics.
Yes.
Nitric oxide synthase, they help in that molecule generation that is nitric oxide,
Yes.
which has a lot of roles to play. Now, when the heme enzymes, these are basically heme enzymes, they start malfunctioning. So, as a porphyrin chemist, as a bioinorganic chemist, do you think that this kind of porphyrins, because inside they are like a polymeric sheath,
Yeah,
inside
yeah,
in the
yeah,
body,
yeah.
in the 3D system. So can these porphyrins be fitted in vivo system and work,
Oh,
can do the xenobiotics without imparting toxicity to the healthy cells?
I think many of the confused pulping chemistry is mesoallyl type, but initially beta alkyl type, just like a regular pulping. Because of some difficulty synthesis, not so much developed, but definitely we can have a quite similar structure of pulping. Only difference is in carbon. Then we expected that we need to ion metallation. Ion metallation is already established, but some reactivity may be um, ion is actually first easily occur reaction is inner carbon is easily oxidized. So CO ion, like a bleach, forms. So sometimes it's help for the medical application, something like that. Some people don't like ion too much for photodynamic therapy like that. So the capture ion is probably much easier than the regular poppy because of inner carbon. So that's control of the concentration of ion metal might be possible, but I'm not quite sure.
Side input
Yeah, yeah,
receptor.
and
Because sometimes in the 2D system also, these porphyrins are doing very good photodynamic therapy,
yeah, yeah, yeah,
but they are again killing the healthy cells,
yeah, yeah,
or they are not able to, they are, so their use is sometimes
yeah, yeah.
very
And
difficult.
actually, put that it's not my group work, but initially we did the photodynamic therapy.
Yeah.
Silver ion is a highly toxin production rate, but the data on that South Africa's Teberos group has more tin compound inside and antimony like that. They are very efficient for the application of the photodynamic therapy. Um, I, at least the cell level, it's very work different cancer cell.
Cancer
Yeah,
cells.
yeah.
Okay, thank you so much. Any more questions?
Yeah, yeah. Okay, so we have a 18 pi electron, 22 pi electron, 38 pi electrons, and 42 pi electron system
Yeah, yeah, yeah.
for different type of extended power frames.
Yeah, yeah. Expanded one.
Yeah. So
Okay.
in every cases where we able to see that pentafluorobenzyaldehyde in most of the cases we
Oh,
have
yes, yes,
used.
yes, yes, yes,
So
yes.
is there any other aldehyde is operating? It is
Oh,
possible,
uh,
or it is because of the stability of this particular ring, pentafluorobenzyaldehyde is the
and
best.
yeah, methyl one is okay. And the reason why we can get protein very easily is that if we use a benzaldehyde like that, it's a polymerization reaction. Pyrrolaldehyde. It's if it's you can see a lot of polymer like that, but TFA something it's break sometimes, and that is uh, pyrrole oligomer is wrapping like this, and if we closer to 4, it's attack ring closing occur, but mostly break. Then um, even the benzaldehyde like that, it's formed as 7, 8, 9 because before oxidation just mass spectrum show. But if you run the reaction longer, then finally reach the tetrapyrrole system. So the confused porphyrin is also similar. If you increase the acidity, um, tetrapyrrole ring is still formed even ring opening occur. Closing, opening, closing, opening. There's, oh yeah, alpha to beta linking occur. So if you follow the time course of reaction, initially porphyrin increase, but time goes on decrease. Then confused porphyrin increase. then go. So timing is quite important. That is controlled by the acidity. But if you use a pentafluor, such break not occur. So continue, continue, continue. So we can get, eventually they have linked, then stabilize, stabilize.
And if I able to confuse the porphyrins,
Yeah.
what are the what are the property it will changes?
Property. Once after isolated the ligand, then first we check the absorption spectrum, but the methylated, then definitely it's have the carbon metal bond, and also the ring sometimes change by if one you can see dianyl core, trianyl core, and sometimes we can just remove the one of them. There's a carbon, then it's like a contracted one and regular one. So we can manipulate the metal core as we want. So still, it's very infant stage, so waiting, so many applications, but I want to, somebody want to do that, not, I want to.
Mean to say unconfused for
Yeah, yes.
Professor Furuta, I
Yeah.
have some question,
Yeah.
some random thought, because I'm not a bioinorganic chemist. Just I'm trying to understand, because these porphyrin systems are very exciting system,
Yes, yes.
because so many
Yeah.
biomimetic functionalization. So all the experiments, all the characterizations are done in solution phase, in vitro phase, right? So just trying to understand that, have any literature report, there is any literature report that if you put this system in a cellular condition, say mimetic condition, in a very high crowd,
Yeah.
so how the system start to behave, or how different it is from a in vitro studies, like then like what kind of property changes you can expect, and the system trying to behave, is there any literature report? Because as a cellular biologist, I trying to understand that if we mimic that condition and put this porphyrin ring in that system, then there is any report how that try to behave, like a characterization.
But it's generally a porphyrin analog chemist making that compound more electrolyte absorption by peripheral fusing something. They're simply expected that in the cell level, just put in the solution compound, then it's introduced into, because of some lipophilicy, then irradiated light, then singlet oxygen appear, then kill. That is a quite simple scenario, and I think that it's quite severe, even confused porphyrin. That like, but probably
I think, Dr. De, the same question I asked.
Yeah.
Porphyrins have been used for photodynamic
Yeah.
therapy localized.
Localized, yeah.
But whenever you go for the inside the cells,
Yeah.
they try to do some of the lysis.
Yeah.
So that's how till now porphyrin are not going into the in vivo system. But maybe porphyrin conjugated with some other system to mimic the sheath which is present inside may do. But it is still
Yeah. It's
far way
still do that.
far way to
Yeah.
go. Because even in 2D system, if it works, 3D system.
Yeah. So input, output,
Yeah.
we know, but inside in black box still
It's
box.
very difficult.
Yeah.
Thank you so much. I hope other questions we can have in the lunchtime. Acha, once for the student, Dr. Partho. Yeah, please. If you can. Our faculties and students are very interactive.
Good afternoon, sir. Sir, actually, I have a doubt of this slide. When you increase the size of porphyrin ring, increase the porphyrin ring size, the Q band is increases. The wavelength is shifted, higher wavelength, can be rate shifted.
Yes.
So, but from this graph, the Q band graph, the all peak height are same. So I have a doubt. I don't understand actually.
These are all Soret
This
bands.
is a Sore band. The Q band is this one.
Q band is different, na?
Yeah, Sore band usually
He's
420.
telling about that pi star transitions.
Okay.
Yeah.
Okay. Sir. Thank you, sir.
Thank you so much. Thank you so much,
Okay.
Professor, for your excellent talk and enlightening us about this. Before we start the next talk, since we work as a team, I should introduce you, Dr. Shruti Khanna Ahuja, who is an important part of the team, who has been anchoring from the starting of this international symposium. I must say that she is a assistant professor in biotechnology after having completed her PhD from IIT Kanpur with Professor Verma, Sandeep Verma. She has joined as NDP in PDF and as a CSIR pool officer in IIT Delhi, and she has joined our university in 2022, August. But she has been actively working with us, and she's the person who is very, very proactive, actively involved. Even though she had today exam duty, she managed that so that she can be an anchorer for our conference. And she's also working to develop biomorph, because MOF got the Nobel Prize this year. So I must mention her, that she, along with my group, so we both recently got a paper, and this is because of our student Bani, who has developed few biomorphs where we say that morph have toxicity, but if we change the organic ligand with, say, arginine with NMA, muramic acid, then their activity and bioactivity will increase. So Shruti Khanna Ahuja, although assistant professor of biotechnology, as a collated team member, has taken this agenda to come up with biomorph which can combat antibacterial resistance. I forgot to introduce her, but she is very much a big member, big important member of our team. So that's how. And now on to you.
Okay. Thank you, Professor Furuta. So, although the talk is about confused prints, so I hope everybody enjoy the confusions. Okay, thank you, Professor, for accepting our invitation, visit our department and give such exciting lectures, particularly the organic chemistry part. So everybody is enjoy. Thank you very much. So we'll facilitate it.
Yeah.
Okay.
Just start.
Okay. Okay.
That you have time with Ranjan design this, and we are happy to have you and him there.
Okay, so now next lecture, obviously I don't need introductions because he's my own supervisor. So I think everybody know, particularly in India, bioinorganic chemist, well-known bioinorganic. I am really honored that I introducing my PI. And obviously he has uh, done PhD, everybody knows, postdoc and other things. So he is basically, if you see the porphin chemistry, any papers is coming, that is Professor Rath, for sure. So Professor Rath is working now, although I work in monoporphins, now Professor Rath is completely removed from monoporphin to multi-hem porphins. So initially I started the monoporphin only. Okay, so with this.
Yes, several awards and honors. Many this year we have received.
Okay, so looks like they know. But then, anyway, thank you very much for inviting me. I am actually honored and privileged to be here. And I will not take much time because you are running late and also you are waiting for lunch. Okay, so my students are also, like hungry. Anyway, so do you have a pointer? Please. Okay. I can change the slide here, right? No, I have to use this. Don't have. Okay. Um, I will be telling something, a story today, and the story of our activity at IIT Kanpur. And the story started 20 years back when I joined IIT Kanpur as an independent faculty. Let me tell you that I'm also a bioinorganic chemist, and as Professor Fruta was mentioning, and when we go and teach bioinorganic chemistry, heme chemistry, we are teaching these things like, oh, I know, Mr. Puruta was using this, or you have something? Or can I get it? I have it in my bag. I'm sorry. You have changer also, right? You don't have changer? Okay, then it is fine. I thought. Okay. Oh, I'm sorry. Okay, so, but 20 years back, we have started a journey with multi-heme proteins and enzymes, which was developing, which still under development. Lot of biologists had started to make isolating this, and our group is the first group in the world who started looking at the molecular level to understand that why multi-heme enzymes and proteins are designed. Okay, and these are some of the structures. The interesting aspects of this multi-heme is like these heme centers are linked to a single polypeptide chain. Like in Deepavali or Diwali, we decorate our houses with the bulb. No, in one, what is that called? It was decorated, and you see that in one wire there are small bulbs are there. So it is something like this. And then we try to address these important issues that why did nature design some such multi-heme proteins and enzymes? What are the advantages? Okay, and this was being said that it's a complicated one because these heme centers are talking to each other, making their investigation complicated because there are so many heme centers. So you do any spectroscopy, it is difficult that which one is coming from where. Then we looked at that what are the simplest multi-heme known. Simplest means the diheme. We looked at that diheme cytochromes, it does the same job as what monoheme cytochrome does, but it is extremely fast electron transfer. Diheme cytochrome C peroxidase, it also does the same job as peroxidase does. What peroxidase does? Peroxidase decompose hydrogen peroxides, okay, because it is a toxic. And this diheme cytochrome C peroxidase is actually, make it like 10,000 times faster compared to the monoheme. So it looks like that PC circuit's magic. Okay, and it looks like magic. So what is the story behind such magic? That was our thought, and we try to understand it. I will not discuss all these things because we have made these diheme cytochromes synthetically. You can see that we link it by synthetically we link it so that in solution they cannot go far. And it is interesting to note here that look at this is the diheme cytochromes, and look at this is synthetic diheme cytochromes. Not only this separation, iron-iron separation is same, the spatial arrangement and the orientation of axial ligand, everything is same. So we are confident that we have made a synthetic mimic of diheme enzymes. Now, why people do it? People do it because at synthetic chemist, you can make large number of derivatives, and so that you understand their system much better. And another thing is that proteins, you don't know what is the role of the protein. You don't know what is the role of these metal fragments. Okay, so we wanted to understand. And that's what bioinorganic chemists try to do that, synthetic chemists. And one can see the effect of these interactions. You see this monoheme and diheme. Look at that heme center, which is perfectly planar here, become distorted. And their redox potential also get changed, their property get changed. So a lot of things. I like to take your attention to a simple, how such simple interactions change property. For example, when we put a double bond, these two rings are far apart. Okay. Now, and look at their property like electronic structure, spin state. But when you put a single bond, what is happening? Two ring can come closer because there is not, this double bond has an orientational issue. They cannot make these two ring coming closer. And when they come, when they are allowed to come in closer, and see all electronic structure get changed. The spin state get changed. Look at here, that axial ligand perchlorate intermediate state, right, phenol high spin, it completely getting inverted. It's so powerful, this interactions. So basically that to him coming closer, it looks like a small, but it does a large impact in the electronics, because they able to interact, and the changes are very large. So I'm not going to discuss this, and I will just keep this with this shortage of time. And we looked at these diheme cytochromes. I will be talking today a enzyme and these diheme enzymes, and we try to understand their design principle, why nature designed these two centers like this, and then how we can implement our understanding to the laboratory. So I will tell you a story. But before I go to discuss that, let's see this diheme cytochrome C peroxidase is actually designed to protect the toxic peroxidase. It is so efficient, 10,000 times faster. This is what is happening in pathogenic bacteria. Pathogenic bacteria, we try to kill them by hydrogen peroxides, and over the years, they have made a defense mechanism to protect themselves. Okay. So this is where the diheme enzyme, another diheme enzyme, MAUSI, and you see the two centers and a tryptophan which is placed in between. And this tryptophan is supposed to be responsible for the communication between these two rings. Otherwise, how they behave like a single unit, they must be cooperating each other. And what it does that 2 electron oxidation and this iron 4 oxo, bis iron 4 oxo, and doing this kind of CC bond formation. And so this is what is being believed, that this electronic communication is happening through the tryptophan. So tryptophan is getting oxidized and reduced, and thereby communicating the electrons faster. I like to take your attention to these issues, like this iron 4 oxo is quite stable and at room temperature. This is very unusual in the sense that we know that monoheme peroxidase catalase cytochrome P450, where it generates this iron 4 oxo, it is very unstable. It only stabilizes at 77 Kelvin for few minutes or few seconds or few minutes like that. But here it is stable at room temperature, fairly stable. And you have two units, and there are two possible sites of oxidation after 2 electron oxidation. One is that the organic ring, porphyrin ring, another one is metal. But only metal center get oxidized, not the ligand center. So this design has something to do. And I like to tell you a story, our understanding about this design principle. Although I'm not going to discuss in details, the relevant papers is there, and this is not the time and place to discuss in details because this is a mixed audience. So I will try to tell you a story. So we looked at this design and to understand that what tryptophan is doing, how tryptophan is communicating. So we have made a large number of derivatives of these diheme, and in sometimes and then we do perform the exactly the same two electron oxidation, very selective two electron oxidations. And what we could find that electronic communication is happening which generates the low energy band, and this has been found that after two electron oxidation they change the geometry. The cis converts to trans, and also it is not a regular trans. It is something very unusual. Why it is so unusual? In order to facilitate the electronic communication through the bridge. You see that two ring has pi cation radical, and this is the way, like we call it, it is p prime form, it is u form, and electronic communication is happening through the bridge. So basically, if it is a pure trans, the ideal trans, then there is no communication through bridge can happen, although they are having the pi cation radical. But after two electron oxidation, the geometry gets changed, and so this is where the electronic communication happens. So this change in geometry is basically needed to make this communication happen through the bridge. Okay, we have done a lot of work, and I am not saying, indeed, you can actually communicate from one center to another center, although this is a tetramer, which results in, you see that large intense NIR band and electronic communications happening from one ring to another. Coming back to the story, that when we change the metal, like large number of metal being used as a synthetic chemist, and all two electron oxidation, only the ligand that is getting oxidized, not the metal. In biology, in diheme, it is the metal that is what is getting oxidized. However, when we find that it is a double bond and it is when actually ligated, then it is, that's 4 electron oxidation, and then it is very stable. We call it, like I teach the students, that if I provide you a hot samosa, and if you hold it like this, your hand will burn because it is hot. So you can, you can disperse the heat by putting it like this exactly. The dication diradical become very stable rather in the room temperature because of these communications, which is very stable. However, when we use the selective two electron oxidation to this system, we found a situation where in one case where metal get oxidized, in other molecule it is the ligand get oxidized. Indeed, in the X-ray structure we have two molecules in the asymmetric unit, and they are different. One is metal center oxidized species, which is diamagnetic. Another one is the ligand center oxidized species, which is paramagnetic. Both are in equilibrium. You can change this equilibrium shifted to one direction to another direction by external stimuli. And indeed, these two structure one can see in the naked eye, and they can able to distinguish that they are different. Two molecules in the same asymmetric unit. However, when we have this single bond where they can communicate, it is the metal which is getting oxidized. So we found the first time that metal center can be oxidized selectively, not the ligand, but communication is missing. In order to extend our work or hypothesis that whether it is really the case, we have extended the work with the silver. Why silver? Because silver porphyrin is known, well documented, to have the ligand center oxidation. Then what we have done it, we took the disilver system, and we have done again the selective 1 electron and 2 electron, and with a surprise, we could find that only metal center is getting oxidized. Indeed, we have also discovered on the way that first silver 3 interactions. And why it is so important? Because it gives an unusual color property because of the metal to ligand charge transfer. It's a beautiful band at 540 nanometer. Beautiful colors are coming out of that. We have extended this work and I am not showing it, but this is something very interesting in the sense that two aromatic ring cannot be at the top of each other because they will repel each other. Two benzene ring cannot be at the top of each other. Two porphyrin ring cannot be at the top of exactly each other because they will repel each other. Okay, in order to make them stabilize, they have to have slip. Okay, and here they are exactly on the top of each other. And then we have investigated, and there was the silver 3 interaction. Actually, a lot of people are following our work, including Dan Nocera of Harvard. And you see that their first scheme, they put our work, which is highlighted here. And this is the first silver 3 metallophilic interactions. They have extended this work to coral system. Anyway, we looked at then, copper, because copper is known to stabilize copper +1 and +2. Copper +3 are too, unstable in the biological system and too oxidizing. Then we looked at, again, Dan Nocera has, even coral, Dan Nocera has shown that it is actually copper 2+, not copper 3+, although coral supposed to stabilize 3+ state because 3 NH proton can be deprotonated. We are talking about porphyrin, which actually stabilize copper 2+. And indeed, we have found that when we use this double bond, it is the ligand which is getting oxidized. However, when we use the single bond, as per our previous results, we supposed to oxidize copper 3. Indeed, this is what exactly happening. It is the copper 3 which is getting stabilized. So look at how bridges change these electronic structures. Okay. And then in the biology, it is the iron 4 oxo in the diheme, which is stable, and indeed we are able to reproduce the result with iron and cobalt, where it stabilized with iron 4 and cobalt 4. And let me tell you once again that these diheme enzymes, that after 2 electron oxidation, this iron 4 oxo, it is 10 minutes in mousy, and our synthetic analog also, it is very similar. It is 13 minutes stable at room temperature. We have done lots of studies to prove that it is iron 4 oxo, and we have recently published the first synthetic diheme stable iron 4 oxo, and this is the cover page of JSCS article. Indeed, we are able to demonstrate that the cobalt 4 oxo, and also it is stable, and you can see that simulated and experimental LIPR match perfectly. So what is our understanding from this study? That if in the mouse G, there are 2 centers, and this is iron 4 oxo, means metal center getting oxidized. So exactly same thing is happening when they are unable to communicate. It's a metal center getting oxidized. However, once you put a double bond, then it is the ligand which is getting oxidized. So it is interesting, like two heme centers, if they are far, it is the ligand center oxidation, and when you bring them closer, it is the metal center getting oxidized. Separate them, again ligand center oxidation. So it is like a fantastic how nature can change the electronic structure. So we believe that it is essential that two centers, two heme centers are side by side, but not communicating to each other directly. Because if they communicate, then it is the ligand center that is what is going to oxidize. So we have done lots of reactivity, oxotransfer. Since this is fairly stable, we then try to make how you can make it more and more reactive. Indeed, we found that by putting a hydrogen bond, you can elongate this iron 4 oxo and you can make the reactivity 11 times faster compared to non-hydrogen bonded things. I'm not discussing in details, but then we looked at that, we understand that biological design, why it is designed like that. Then we looked at that how diheme enzymes like mousy behave like a single unit. Okay, because there are two centers. And just proof of principle, we have utilized the Diels-Alder reaction, which is known for ages. And there are two centers, two heme centers, they are communicating through the bridge. And then we explored this, that the simple Friedel-Crafts reactions. And what is happening that these reactions are much faster compared to the monoheme, and there is a cooperative effect in between. We have investigated in details, including DFT study. So what is basically happening that ketone actually ligates directly to iron centers and thereby facilitating this Diels-Alder reactions. And indeed, we have identified each and every step spectroscopically in solution. And so what we propose is all the stable intermediates. So basically this communication is happening through the bridge, and that's why they behave like a single diheme unit. Indeed, we then extend this work from iron to cobalt, and with a surprise, we see that this catalyst loading is much lower from iron to cobalt, and the temperature is much lower. Indeed, the time which is required 10 hours for diheme, dicobalt, it takes only 2 hours. And with a surprise, we saw that these all intermediates had been isolated and spectroscopically characterized. So this is what is the reason, cooperative catalysis, that here one aldehyde binds to the iron center, here both the aldehyde binds to the iron center. It is not only that, this cobalt 3 and cobalt 2 pi-cation radical, they are also electronically, they are changing, they are under cooperation. Indeed, here it is a unique features of metal, ligand, and bridge are undergoing cooperativity, and that makes this catalyst is a extremely efficient catalyst. And this we have just published recently with a cover page with a chart showing that they are cooperative catalyst, and we found that dicobalt is giving that extremely high yield compared to the di-iron, monocobalt, and other things. So cobalt, because in cobalt you find this extensive cooperativity between metal, ligand, and the bridge. Then we extended, actually, I'll not take your time much. And so what we are trying to do, this is another simple catalysis reaction. Why we have designed it? Because you have two hands. So what we believe is that if you can do something in one hand, if you put another hand cooperatively, then you can do miracle. For example, in one hand, I cannot pull this up, but if I use two hands, I can easily do it, provided the two hands are utilized cooperatively. It should not be 1 plus 1. This one hand here, one hand here. There is no cooperation between them. Indeed, what we have found, this particular reactions, what we found that one iron centers bind to one substrate, another iron center binds to another substrate. They come close and things make the reaction happen. And then once this happens and then it produces the product and goes back the catalysis. So something like this, that one hand, one substrate, another hand, another substrate, different substrate. And they come close and the reaction happens and the product release and then they go back. So that's just like this. And we have all spectroscopic proof for each and every step I have written here. Okay. And in situ, we have monitored and we have proved that the substrates are binding stepwise. You see two different substrates. Otherwise, this reaction would not happen. Okay, reaction happens when they come close. Okay, and this metal coordination is required to activate that substrate. So here also spin state. So these two hand binding are making this possible because of the cooperativity between these two hands. And that's what we have tried to demonstrate it. Okay, so what we are trying to do it at IIT Kanpur is that the reactions that are unusual, that should not happen, that generally do not happen, making it possible. In other words, if something, we put all metal, ligand, bridge, one ring, two ring, three ring, and putting them together and making it a very strong catalyst. Just like, our many goddesses has 10 hands, like Durga has 10 hands. So it was necessary to make it very efficient and very powerful weapon to fight this. So I'll conclude here. So what we think is that why do nature design multi-heme? So because like for diheme, we have seen that presence of more than one heme center provides the nature with another tool to modulate structures. In one hand, what you can do, if you put another hand cooperatively together, you can do miracle. And this is what we have found, we have demonstrated. This is probably the reason why nature has designed multi-heme proteins and enzymes. Okay. And what we found is that we discovered that these interactions has been demonstrated as a new powerful tool to change the electronics, which was not known earlier. We try to understand the nature's design of diheme enzyme, as I have demonstrated here, the diheme mousy, and bioinspired cooperative catalysis with super efficiency, because if you can put things cooperatively, it can indeed do miracle. So I put all my PhD students who are already graduated, because you can see the Ranjan Patra is number 2nd here, and I have collaborators, I have postdoc. I'm grateful for funding, J.C. Bose Fund and ACRB Star. These are all actually award, and I'm very fortunate to receive those and to fund my laboratory. And this is what is my current group members. Maybe 5-6 months before this picture was taken. And because of their work, I am here standing in front of you. So I thank them first. I thank the funding agencies to fund my laboratory, fund my research, and I thank all of you to listen carefully my talk. And I thank the organizers for giving me an opportunity to stand here in front of you. I think I am finished in time, and thank you very much. I'll be happy if you have some quick questions. Yes, please.
It was a very wonderful talk. I have few questions that when you are making this like the dimer kind of thing, dye kind of thing, the porphyrins. So what's the yield? The yield is a problem with preparation of dye, like porphyrin.
Yield is a problem. Of course, yield is a problem, but we make it to understand something bigger. So problem is there, but we have to work on those problems.
Okay.
The coming here is also a problem, but you have come here to meet all of you, to you also. Right. So yeah, this kind of targeted synthesis will take time. Targeted synthesis will take time, and I remember how we have started, and I don't like to look back. We struggle, and that's why I would able to stand in front of you because of that struggle. Struggle is very essential. Those who are young, I must tell you, is that if you struggle, that that ensures that you reach high. Without struggle, nothing can be possible. So struggle is very, it's a blessing. We struggle till now. We struggle, and probably whatever I could do, whatever I could achieve because of my struggle.
And one more thing.
Yes.
The connector which you have taken, right?
Yeah.
So that has a very big role to understand
Yeah.
which particular thing is getting oxidized.
Yeah.
Now, when you are having CH2, where there is no double bond, you have the metal center oxidation.
Yes.
So if you increase that
Yeah.
length.
So let me tell you, it's a wonderful question. Yeah, we have made several such molecules, increasing, decreasing, all this. But why particular that connector I am saying? Because that perfectly match with the diene enzyme, the space, the separation, the design. I have shown you. Okay. Second is that makes us to understand the law of bridge. Like if the two ring can communicate each other, then the ligand, like pi cation radicals able to communicate. If you stop the communication, then the metal which is getting oxidized. So this is what is our learning.
Yeah, for the metal only, metal center oxidation.
Yeah,
there is no there is no communication as you
no,
were
there
saying.
is no communication.
So there the length of this connector, if it's increased, then you
Let
think
me
it
tell
is
you, this is what I have also said. Like if you increase it, then it is the ligand center oxidation.
Okay.
Okay. So this is behave like a monoheme.
So
it's a
it is
ligand
for
center oxidation.
single.
When you are bringing them closer, then metal center getting oxidized. Okay. So linker role has a length has a meaning. So we believe, and it is what we found in experiment, that these two rings need to come close, side by side, not communicating directly each other. Because if it is side by side, then only metal center getting oxidized. Okay. But if you make them separate well, this is the ligand center oxidation. So you can design the electronics.
One more
Yes,
question.
please.
I have seen the porphyrins getting their role in as a catalyst in
Yes.
photocatalytic reactions also.
Yes.
So for the dye one, do you think it is greater activity which is going to give as catalyst in photocatalytic reactions?
Yeah, I think so, because I am not what I have shown here. It is the proof of the principle. Proof of the principle we have shown. That how cooperativity can change the reactivity, can change the yield, can change some reactions which is otherwise not possible to have. Okay, that is a demonstration. And yeah, I'm 100% sure that photocatalysis, other things is also going to happen. Actually, we are doing it.
Yeah.
We are doing it.
Okay, thank you so much.
Thank you so much.
Nice talk, sir.
Yeah.
Very nice talk. Just one question.
Yes,
that
please.
you told iron 4 oxo.
Yes.
It is stable at room temperature.
Yes.
To like 30 minutes. Right?
Huh?
30 minutes, right?
13, 1-3.
1-3. So what happened after that?
Huh?
What happened after that?
Oh, yeah.
I mean, it
What
transformed
happens?
to what?
So what happens? How you keep it.
Okay.
Okay. If another substrate comes in, then this oxo transfer, this iron for oxo, whatever it does, even at low temperature, is reactive.
So it is in solution.
Which one?
That iron 4 oxo. It is a
Yeah, it is in solution. It can be in the solid state also. It is reactive. It is, although this is what I mean to say is that the reactivity is same, whether it is a monoheme or diheme or triheme if you do it in future. The reactivity, same oxo transfer, same kind of hydride transfer can happen and should happen and will happen. What I am saying is that this reactivity becomes sluggish, slow reactivity. Okay, so this is a reactivity because it will change to, if substrate solvent can
So
be
it can dimerize
oxidized.
also. It may
Yeah, it can do many things, many things.
oxidimer. That's something.
It can do many things.
Another thing in the catalytic cycle, you show the very nice cooperative catalysis.
Yeah, which one? The last one?
Suppose last one.
Okay, very good.
So basically iron.
I
cobalt,
can go back
yeah.
to this.
Iron and
What
cobalt,
happens, it's
that
not
is
going.
activating the both substrate. One is ketone, another one is.
No, it's
So I'm wondering,
yeah,
because it is a homogeneous things, and you have the Brownian motion. So it
yes, that's a very interesting
it
question.
may possible that instead of having the intermolecular,
Hmm.
intramolecular, it can also happen the intermolecular, like one part is in one molecule, another part is another molecule.
No, that is always a probability, no?
Probably, right? Yeah.
No, issue is
So
that
like
whatever you said is all correct. Say, for example, you can say that this one substrate binds to one.
Yeah. It's
there.
there.
That is always there.
But it's most likely.
Which one?
This one.
No, this is not most likely. This is, we have all experimentally, we have proof.
Okay.
We have all evidences because these are all, we actually, this is what is another strength of us is that we monitor the reactions in solution by using EPR and paramagnetic NMR.
So in situ study is done.
Yeah, in situ study, and that makes us
Okay.
to tell, otherwise how I can tell?
Yeah.
It's just like, actually most of the catalyst people, they don't look at because they are unable to do it.
Yeah.
Because of our, we are expert of that, we are able to do it, say, for example, we able to spectroscopically identify all sorts, all intermediate that is drawn here.
But also that is the also problem. Whatever you are seeing in the spectroscopy, that doesn't mean that that is the active part in the catalysis.
No, that is not the active part in the catalysis, but that is,
right.
Say, this is.
What is the principle?
No, let me tell you.
Jack Halpern principles. Jack Halpern's reactions, right?
No,
the majority you are saying, that is not the active part. The minor is the active. That may possible.
Let me, you have said something. Let me tell you. That you will not see each and every intermediate. It's not possible.
Yeah.
What we talk about as a chemist, we talk about some quasi-stable intermediate. Those you can monitor them spectroscopy. You cannot see everything. Nobody can see it. Not isolate, you can isolate.
Isolate also give the problem.
Tell is stable. See, none of these things you can isolate. Because they are not that stable.
Yeah.
You can monitor. How you can monitor? Let me give you a tool. Then how you can do that? For example, this molecule. How I can get it spectroscopically? Like this molecule, high spin, when it binds with the crystal. So NMR will be very clear, and NMR all these things will be coming outside the diameter. Okay, which confirm you they are binding to the two other spectroscopy can do that.
Yeah.
And EPR. So by combining NMR and EPR, you can confirmly say that this is what UVB is all spectroscopy doing. So this is not possible if you are not spectroscopy.
Okay. Yeah, okay, yeah.
And you are right that not all these things can be visible. Nobody can claim all. Yeah. I'm not claiming certain.
No, that's fine. Thank you.
I hope I make.
Yeah. That's fine. Absolutely fine.
Since the intermediate which is participating.
Okay. Right. Yes. If we have time, I don't know.
Sir, excellent presentation. Sir, you mentioned beginning that you were able to get the crystal structure asymmetric unit has a two different. So you checked the bond lengths and they were short for the low spin and longer for the high spin. Is it that? Hmm. हाँ हाँ cobalt है. Okay, that one's the. So now हाँ, so cobalt to हाँ, हम्म, हाँ हाँ, हम्म, हम्म, हम्म. Yeah, how they are together in the asymmetric unit will be interesting to see. How they are together, coexist in the same asymmetric unit, because I think you showed it separately. So I was just curious to know. हाँ.
That I'm also. So you can look at it's a top view and side view. Irrespective of the distance, what happens when there is a communication between the breed, you see that look at this breed, it's a top view, and here look at
Yes.
breed versus.
Okay. Yes, sir. Correct. But I'm sure this you would have not seen for other system. This is very specific maybe for this one. Cobalt. Okay. But having cobalt and switched actually. That possibility exists. Otherwise that is not there. Yeah. Yes. So magnetism also can help us here, right? That diamagnetic parameter. Okay. Hmm. 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 Excellent. Very nice, sir. Thank you, sir. Thank you very much.
Yes, please. Yeah, these are fairly stable. We all working with stable molecules. No. Photo-oxidation, anything can happen. You expose a deep light, it will break it. And indeed, not only porphyrin, these are our molecules. Like any molecule, we can do fine light for a long time, it will break it. And porphyrin is not so big.
Yeah. So, Professor Rath, it's a very interesting talk. So, like most of your system, like with the spacers and the configurations, like one on, the pyridine ring on, double ring systems. So, are these highly conductive as well? Like if a metal ion is put, like let's say alkali metal ion, what will be the chemistry there? Like, will it move from one ring to another with the bridging, the amount of pressure that it.
No, actually, communication. Say communication. This we have done extensive work on this, looking at these communications. Okay, but then when it is pure trans, this communication through the bridge is very small. So bridge has to change. Like when we have worked with the pi cation radical, then the bridge is changing. The structure is changing completely to make it possible. For example, if I want to come to this chair, it is very difficult. So some way has done, like structural change has done to move from one ring to another ring.
So I was trying to know whether any, let's say alkali metal ion, if it is put, will it be very dynamic, like it will be moving at a time scale which cannot be frozen?
I don't know. I have no idea. Dynamic means metal ion will come from
Move
one ring
from
to
one side to another, go to another ring, then come back.
possibly not, because we have not tried, but possibly not, because these rings actually binds the metal very tightly.
Okay.
Professor Pruta was showing that chloride. Hmm. But chloride is size is bigger and it is outside. Okay. But these metal ions, they sit in the cavity and very stable.
So there is no possibility of that.
I will not say possibility is not there, but I probably think that these are all stable molecules. I probably think, but we are not trying.
Okay, very interesting.
Thank you. We also look at the surface property and other things we also look at. Yeah, this has happened. This has happened. You are absolutely right. We have published maybe last year on surface, and where we could find something unusual stabilization because of the surface. Ha. Ha. Thank you. Thank you.
Okay, thank you, sir, for a excellent bioinorganic actually lectures. So all the metals, so you can able to find the play with the metals, oxidation state, cation radicals and other things. So it's a excellent lectures, and thank you, Professor Roth, for accepting our invitation and visiting our departments. And now it's the time to give the memento.
So please give a big round of applause. Here, ma'am. Please, please continue with the applause for the fantastic lectures. And I must take an opportunity to mention one thing about Rat sir, because I happen to be from the same institute in the adjacent lab. And I was just telling to Dr. Pooja that I have never seen sir going out anywhere. He used to sit whenever we used to leave at night from our labs. He was always there in his cabin. Students were also there, but he never used to yell or shout at them. But yeah, he was there doing his research work there. And that is quite evident from the way he has presented his work.
I can tell you can able to find Professor Roth at 2 a.m. also. In the lab.
सर आप लोग आगे रहिए आप लोग आगे रहिए
One of my students, although I could not fly directly, he was so he had a fantastic
खड़े हो जाएंगे सभी लोग ना आप लोग आगे खड़े आप लोग आगे all the further advance one student is coming right one student is coming right
I hardly find somebody like because no, I have not seen.
It's not possible. That's what part of group practice.
रमेश जी ऑफिस कब तक है पीछे हाँ वो लोग का काटने नहीं चाहिए
methane plus oxygen into methanol or acetic acid, there are some challenges out there. And challenges comes from kinetics as well as thermodynamics. So kinetically, first of all, the methane CH bond is very inert, is very strong, 104 kcal per mole. CH4 is a non-polar molecule, tetrahedral structure. It is a non-polar. It is very difficult to polarize the methane or CH bond to activate the CH bond. And not only for that, there is also the thermodynamic challenges, and that is that once you activate the methane and converted this CH bond to OH bond, it gives the methanol. That intermediate is very difficult to stabilize because in the catalytic conditions, it has the tendency to further over oxidations. And ultimately, it will give the carbon dioxide. That is a burning. So it's very difficult to control, to stop the reactions in the middle and with high selectivity. Selectivity is also an issue. Otherwise, overall industrial output cost will be increases. There is also some separation issues will come. I'm talking about in terms of industry, not just like producing papers. So if you want to, and if the transformation methane to acetic acid, then there is one more challenges, that is the CC bond coupling, because the methane is the one carbon, C1 carbon, and acetic acid is the C2 carbon. So basically CH activation, CH oxidation, CC coupling, all have to take place sequentially, otherwise you will not get acetic acid. It's very challenging experiment or reactions. So there are a couple of ways you can activate methane. So I'm talking about methane activation. One is the radical pathway. Just hydroxyl radical. If you just add to with methane, that this radical is a reactive species, it will abstract the CH bond and it will give the methane radical, and then it will react with water, for example, and it will give methanol. That is well known almost like 100 years before. Like if you add the Fenton reagent, hydroxyl radical, that can activate methane to methanol. But the problem in the radical chemistry in catalysis is that you don't have any control on selectivity, because you don't have any control. So if you want to selectively convert methane to methanol or acetic acid, then one of the common way is develop the metal catalyst, which can activate and subsequently oxidize methane to something value added oxygenates. So let me tell you that what are the possible pathways some metal can activate methane. Mainly there are 4 pathways are known. There is from literature I took it. One is we teach, that is the Silov chemistry. Normally we teach in BSc or not BSc, MSc level. Okay, that is the Silov chemistry. That is the electrophilic activation of methane using platinum catalyst. And Silov was a scientist from Ukraine, Russian chemist. Another one, the second one is the sigma bond metathesis. If the metal ion is electron deficient or D0 metal complexes, metal ion, then it can activate methane via sigma bond metathesis. The third pathway is the oxidative addition. It's just like we teach in organometallic chemistry to the student in BSc students. If metal ion is electron rich, then metal activates methane via oxidative addition, and also the methane activation by 1,2 addition is also reported. So now I'm going to tell you that how we can develop highly efficient earth-abundant metal catalyst using metal organic frameworks for methane oxidation. So just an overview of metal organic frameworks. I think many people know and some people may not know. Anyway, so this year, these 3 gentlemen got the Nobel Prize on developing MOF. Professor Kitagawa, Richard Robertson from University of Melbourne, and Professor Omar Yagi from University of California, Berkeley. So why we are interested to working on MOFs to develop catalysis? Because MOF is a very nice porous materials to develop very stable, robust. Stable is a vague sentence. I don't like stable. It's a very robust, single site, monometallic, earth abundant metal catalyst for various applications. So just brief that what is MOF. Okay, yeah, I think some people are also working, like Professor Saikat is also working on MOFs, right? So it is made from metal oxo cluster or metal ion, and these are bridged with is a very simple diagram, bridged by bridging linkers to give a 1, 2, or 3 dimensional frameworks. And normally 3 dimensional frameworks, which has porosity, those are called metal organic frameworks. In catalysis, actually MOFs offers the advantages of both homogeneous as well as heterogeneous catalysis. So first of all, if you look at the homogeneous, that MOFs are crystalline, you can get single crystals, or if you don't get, no problem, you can deduce the structure from powder XRD. It has a well-defined molecular nature, and it has a reticular synthesis predictable structure like many homogeneous complexes. I will tell next slide that what is this. And mob-based catalysts are mostly heterogeneous catalysts, and all we know, we also teach that look, more than 90% industrially used catalysts are heterogeneous catalysts, even though it is difficult to study science on heterogeneous catalysis. Why? Because that has a one fundamental advantages, that is the catalyst separations and recycling is all about the money. So MOFs can provide the both advantages. So in MOFs, this one of the main property why Omoriage is very famous and got the Nobel Prize is that it's a reticular synthesis. Means it has a predictable structure. For example, this is a MOF, is name of the EYO66 zirconium-based MOF. It is made of zirconium oxonodes and it is bridged with bridging linkers to give the three-dimensional framework. If we just increase the length of the bridging linker, then you can see the structure or topology is same, but the pore size is increased. So you can tune the pore sizes by changing the length of the bridging linker, keeping the material basically same. So you can tune the properties, basically you can tune the pore sizes. And this is very important in catalysis. One of the important feature of this particular MOFs, for example, here you can see the nodes. This is the zirconium oxohydroxo cluster. This is basically zirconium oxide. And this oxide you can use as a oxide supports to develop single site catalysts. In industry, there are many oxides. They are like zeolites, zirconium oxide, aluminum oxide. They are used as a support or heterogeneous catalyst. But here you can see this is a support. It is a very tiny metal oxide. It is not like a very polymeric structures. It's a very tiny metal oxides which will be used to develop the well-defined molecular catalysis. So there, next I'm going to tell that how. So our design is that if you just take one MOFs and if you zoom in again, suppose this is a zirconium-based MOF, this secondary building units or nodes, it is composed of oxides. It is based on the high valent metal ions. Now, if you just additionally, if you just install one metal ion, what we are targeting is something like iron, cobalt, nickel, very cheap, earth abundant metal ions. We don't work on precious metals because we don't have money, though not much funding. It's okay. So we are focusing like iron, cobalt, nickel, easily affordable first row tungsten metal ions and those complexes, which if you install it, then this metal ion will be highly electron deficient, which may be. Why? Because these oxides are based on the high valent metal ions like zirconium +4, cerium +4, hafnium +4. Not only for that, one of the drawbacks, means not drawbacks, the problem in homogeneous catalysis that you cannot use the homogeneous catalysis mostly at high temperature reactions because they decomposes. And there are many decomposition pathways. And because homogeneous catalysis normally works at room temperature or mild conditions, but not in a very high temperature, because they can undergo intermolecular decomposition. But here you can do the site isolation. You are fixing the metal active sites in one positions. They cannot interact to each other. Okay, because of the site isolations, whatever the catalyst you will generate, it will be highly robust. I don't like the tell stability. It is a robustness, more scientifically correct. Not only for that, I told also that you can also tune the pores. So you can control the selectivity as well as diffusion in a catalytic reactions. I will also show how. And also the high surface area. So basically in a same material, we'll have very many active sites in a same material within the same pores. So your efficiency, catalytic efficiency will be very high. And the last, as I told, that mob-based catalysts are heterogeneous. So you can easily recycle and reuse for particular reactions multiple times. So first I'm going to tell about the development of a copper-based catalyst using a cerium MOFs for methane to acetic acid transformation. So first I'm going to tell little quickly that how the synthesis and then characterization. The first, the MOF synthesis is quite easy. Whatever we do, we normally don't develop new MOFs. Okay, I'm not not a MOF guy. I'm the molecular person and organometallic guy. Okay, so we chose which is easy to make and which is already known. So it is a very one-step reactions. Just take phenyl benzene dicarboxylic acid. It is called VDC. Heat it with ferric ammonium nitrate for 1 hour in DMF and water and 100 degrees centigrade. You will get a very good crystalline material. It's a 3D crystalline material, and we call it is the cerium EYO MOF. Now, if you zoom in the this SBUs, you can see there is a mu3 hydroxyl groups, the red color. You can actually, if we, what we do, we deprotonate this hydroxyl with n-butyl lithium. This is all about the solid reactions. This is the solid. We deprotonate with n-butyl lithium in THF, so it is the heterogeneous part. And then, so it gives the O minus, and there is simply metallations like organometallic chemistry, coordination chemistry, we do that. We treat it with copper dichloride in THF, and it gives the copper monocopper chloride complexes where it is attached with this SBU. Then we treated with sodium tethyl borohydride. What it does, sodium tethyl borohydride basically interchange the copper chloride into copper hydride, and then we add water. So copper hydride reacts to the water to give the copper hydroxide. So our ultimate target is that how to make the copper hydroxide. There might be other routes also. So after this reactions, we test that by ICP-OES data, how much metal is there. And we found that not all hydroxyl groups are metallated. That is not in our control. We found approximately, it is the reproducible, approximately 45% of the hydroxyl groups are coordinated or functionalized with copper. So this is the crystalline solid. How we characterized, first is the powder XRD, and this is a well-known material. So from the simulated zirconium US66 MOFs, we do the powder XRD, and we saw that up during the post-synthetic metallation process, its crystallinity as well as structure remain same. And this MOF is highly porous. As I told, it is a porous material. Its porosity before metallation is about 800 meters square per gram, and after metallation with copper, it is around 570 meters square per gram. Most important part is that how to characterize the copper coordination environment of the copper ion. So we relied on XFs. Single crystal, you cannot do that because they are the disorder. So this is only one tool we can characterize very precisely is the by XFs, and thanks to RRCat, where we did the XF studies using synchrotron radiation source. So the XFs studies shows that actually this is the dinuclear species, the copper, di-coordinated copper. It is coordinated with, now it is mu4, organometallic chemistry, mu4, O minus, O1 hydroxyl, and this is actually equidistant with all the 6 carboxylate oxygens. And there is this is a well-defined species. There is no no other copper oxides or copper nanoparticles. It is not present. We also did a lot of washings also during the preparation. So once we did the catalysis. That's the target. That for methane oxidations based on our principles that I showed you in the first 10-15 minutes. So we took this catalyst. We used a high pressure reactor like power reactor, and we pressurized with methane and oxygen, very simple. And solvent we used as water because water is needed. I will show you later. Water acts as a solvent. Not only for that, some cases it acts as a reagent also. So then we heated, and then what about after a certain period of time, we analyze the product by GCMS, or also NMR, but that is the last. So just I want to show that there are a lot of reactions we did, and this is the optimized table. So this we found actually in these reactions when we heated this cerium EYO copper hydroxyl catalyst in presence of methane and oxygen, we found actually acetic acid. And acetic acid in the optimization, we found the reaction works very well to give the very acetic acid with very high selectivity when we heated at 115 degrees centigrade for 40 hours of reactions. And when oxygen pressure, the mixture of the gas, oxygen is 6 bar and the methane is about 30 bar. So in this reaction is optimized conditions, we get 1.24 millimole of acetic acid In the beginning of the starting methane is the 42 millimole. If we calculate, that means about 6% methane is converting into acetic acid, and there is no other product. That is also very important. There is no mixture of product. There is a little bit of carbon dioxide and CO is there, that we don't have any control, that is expected, some over functionalizations. But there is no methanol, or there is no ethanol, or there is no other product. So this is actually a very good achievement. We are excited that we are using this MOP catalyst. There is no other report like we could get acetic acid in very high selectivity as well as productivity just from using methane and oxygen. And what is the temperature? 115 degrees centigrade is very low temperature. And in water, there is no other organic solvent is there. It's a direct reaction, just methane and oxygen, we are getting acetic acid. And the metal is the copper. There was one catalyst reported only that time in Nature Catalysis, that was the gold catalyst, and that was much more less selective and less productive. But ours is, that time it was the highest, and probably still it is the highest. So next we studied the mechanism. So what is likely the possible mechanisms, and if that can help to develop further for next generation catalyst. So we also did a lot of control experiment. We just tabulated. It's not a good way to represent, but just I want to tell that if we do the reaction in presence of methanol or ethanol instead of methane, we did not found any acetic acid productions. So that might indicates that probably the methane to acetic acid transformation is not going via methanol or ethanol intermediate. We also found that during the reaction, actually in absence of catalyst, some carbon monoxide is produced. That's expected. Small amount of carbon monoxide is produced, and when we did a reactions with methane and carbon monoxide, we found a good amount of acetic acid. So that indicates that there might be that some in situ generated CO in the catalytic reactions at 115 degrees centigrade, that in situ generated CO is also taking part for the methane to acetic acid transformation. There are a lot of other data I'm not going to show. So it is just like a catalytic cycle I'm just showing, because there are other steps I will show. So this is we propose the catalytic cycle. First, the copper hydroxyl reacts with methane via sigma bond metathesis to give the copper methyl species, and then the in situ generated carbon monoxide coordinate with copper, and then migratory insertion, then hydrolysis with water to give the copper hydride, and then further reactions with water to give the copper hydroxyl regenerations, and hydrogen is produced. And this is the balanced chemical equations, the methane plus water plus oxygen equal to acetic acid plus H2. And we quantified H2 productions here. And obviously here water acts as solvent as well as reagent also. So for this study, we found a catalyst which can directly convert the methane to acetic acid. Very high turnover, very high productivity. Turnover number is 400, conversion is 6%, and selectivity is 96%. That's very impressive. But ultimately, it's okay. We published a paper. But if you want to transform into the industry, we felt that it's still not good enough. We should further develop. So what we did next, that let's change the SBUs with aluminum SBUs, if that can tune the electronic property of the metal complexes. And also let's tune the pore sizes, because pores might have the effect for the diffusion, adsorption, and desorptions. So we used another one MOF that is called the MIL53 or DUT5 MOF. This is the aluminum based MOF that is also very highly robust, and which has a little larger pore sizes than UIO66 MOFs. And this time we used iron based MOF, iron, even more cheaper than copper, right? What we did, that iron functionalized MOF, we also did the similar way. We synthesized in a single step process the DUT5 MOF, then treating with N-butyl lithium, the same process that I showed you 10 minutes before, then sodium triethyl borohydride, and we got the iron plus 3 dihydroxyl species, which is installed under SBUs of the DUT5 MOF. And the characterization, we also did a lot of other characterizations, and this is published work. So the main characterization is the XFs, and XF studies indicates that iron is actually the 6 coordinated distorted octahedral, not perfect octahedral, whatever we found. And this is coordinated with the mu3 oxo. This is from SBUs. These are the L-type ligands, neutral L-type ligands from the carboxylate. And this is the 2-hydroxide and water from the solvent. So this is a 6 coordinated iron species, and also there is no iron nanoparticles present. We, again, the similar way we did the catalysis, there is not much variations. We took the catalyst, we charged with methane and oxygen, and we heated, and then we analyzed, and we found something interesting, that same catalyst actually giving two different products in high productivity, high selectivity, but at two different temperature. So in summary, I'm not going to tell in details. At 125 degrees centigrade, the major product is methanol. And at 150 to 175 degrees centigrade, we are getting acetic acid as a major product. And with high selectivity, the same catalyst, it can give two different products. So basically 150 to 175 degrees centigrade, we are getting acetic acid up to like 81 millimole per gram iron per hour. That is one of the highest so far, with 94% liquid selectivity. And now the methane conversion is also increased from 6% to 13%. 6% was in the copper, and now 13% for iron. It's more exciting for anything. If you do with iron, I get excited because it is iron. And on the other way, if you do the reaction at the 125 degrees centigrade, you get the methanol with high selectivity, 94% selectivity with the methanol, and 90% is overall selectivity. So we did a lot of studies. It is published work. If you're interested, go to the paper. That was in Nature Communication. Yeah. We did a lot of control experiment. And in summary, we found that in this reaction, actually, there are two pathways are going on. One is the methane is converting to methanol. Methanol is converting to formic acid. Formic acid decomposes in situ, give the carbon dioxide and hydrogen. This in situ generated reagent gives the acetic acid and water. We did a lot of control experiment. That is confirmed. Another one reaction is that carbon dioxide and methane, it also gives the acetic acid, and this reaction is particularly very interesting. There are not many reports are there which can react the carbon dioxide and methane to acetic acid, because both are greenhouse gas. Carbon dioxide is also greenhouse gas, methane is also greenhouse gas, and both are giving acetic acid. Is a very valuable product in industry. So we proposed two catalytic cycle. The one catalytic cycle is the hydrocarboxylation pathway, where the iron catalyzes the methanol plus CO2 plus hydrogen to give the acetic acid. And second one is the carbon dioxide carboxylation, where the methane reacts with the iron hydroxyl via sigma bond metathesis to give the iron methyl species, and the insertions of the carbon dioxide to give intermediate, this intermediate, and then the hydrolysis to give the acetic acid. So for copper to iron, that's exciting. It is even more reactive. Productivity wise, it is also good one. So we thought that this is the approach that we followed, and we are still working on for other systems. That is the designing of the catalyst using the SBUs, the secondary building units, basically the oxide supported metal hydroxide. So can you do the other way? Like I told in the beginning, right? I'm not a bioinorganic chemist. So I don't work on, but can I do something like bio-inspired? Okay. Like methane monooxygenase. We know that methane monooxygenase is an enzyme which convert methane to methanol at room temperature. Efficiency is relatively okay. I think 5 millimole per gram catalyst per hour. That is the methane to methanol. It does at room temperature, and it is well studied in literature, and it has the active side has the di-iron core, and the active sides which activate the methane, it is actually the iron 4. But Professor Raut also showed some examples of iron 4 chemistry. So here the active site in the methane monoxide is iron 4. So we can also might do some similar type of dimeric iron complexes. And if you do that and make it high valent iron oxo, that can, may activate, we don't know until we do that. Activate methane efficiently and then convert to something else. So what we chose the similar to like DUT5. The previous one was also the DUT5, but in the DUT5, the linkers were that biphenyl. Here we are using the bipyridine, dibipyridine complexes. It's a bipyridine. So here our proposed idea is that using this MOF, if we can make a dimeric iron dihydroxyl species, then if you react with oxygen, it may react with oxygen and gives the iron 4 complexes, and then it can, we don't know, it can react with methane to give methanol or something else. So we did it. We chose the Mil 253 iron 2 MOF, very easy to make, is a one-step synthesis. Here the linker is the bipyridine functionalized dicarboxylic acid, and we can see like DUT5 MOFs. Here the linkers are the parallel, and they have interlinker distances about 6.6 angstrom. So 6.6 means here, not here. It is in here. So that might be a good enough to make a diiron complexes. So we treated with iron, just simple, is a bipyridine. We metallated with iron dichloride in THF, and then treated with sodium triethylborohydride, and treated with then water, and we found this type of complexes. It is difficult to characterize because especially in the heterogeneous catalysis. So we did with IR, and we saw IR data we have not given, that bridging hydroxyl and terminal hydroxyl is a very weak and poor. It is published also. This is, we found it, but one of the major evidence is the accepts. We can see that the scattering around 2.5, a very strong scattering here. This is actually coming from the iron. We fitted well with the DFT optimized for data, and it is very nice fitting. It actually tells that whatever the material we made, it has about 90% dimeric, 10% monomeric, and 10% monomeric. From where it will come? So we rationalize that definitely this is the material, is a particle, so surface cannot have the dimer. If any iron complex is on the surface, it have to be monomer, and that is the 10% coming from there. And inside of the pores, it is primarily dimer. So we also characterize, we have made the monomeric iron dichloride, and we compare their structural features. So monomeric, what we did, we made the MOF with the mixed linker approach, where there is a 1% of bipyridine and 4% is the unfunctionalized linkers. On those cases, there is no bipyridine linker side by side. And on those cases, we can make the monomeric iron dihydroxyls. And if you see the excerpts, you can see that monomeric, this circle here, the scattering is very intense in the dimeric cases. This is because of the neighboring iron, is iron. Monomeric, it is not there. So we did the catalysis is the same way we did it before. We told 2 times. We found that the monomeric actually is very active for giving methanol, is optimized conditions. We did a lot of reactions, and we found that very much reactive at 95 to 100 degrees centigrade, and monomer gives methanol, whereas the dimer, we also expected methanol, but it is actually giving acetic acid, but at high temperature, that is 160 degrees centigrade. If you do the reverse way, the selectivity is very poor. So it's the optimized conditions. Dimer gives at 160 degrees centigrade, very high selectivity, high productivity of acetic acid. Monomer gives methanol. So we also did a lot of control experiment and for mechanistic studies, and we found that for both cases, radicals are involved. And this is a proposed mechanism. I'm not going to tell in details. And many steps are speculative. We don't have much experimental evidence. I'm going to tell it. Okay. But here we have a couple of intermediates we isolated. We also have the involvement. We found that involvement of methyl radical as well as hydroxyl radicals are there. And we proposed also in this catalytic cycle that this is happening because of the cooperativity. I think 2 lectures was also on cooperativity. Cooperative between these 2 iron centers, which activates oxygen and methane to give the acetic acid. And also the in situ generated CO is also involved for methane to acetic acid process. So in this project, we found that is very interestingly that monomer and dimer is in the same MOF. It is totally giving different reactivity, and they are very selective in certain conditions. One is giving methanol and one is giving acetic acid. So far, this is the summary of all the literature catalyst. Methane to acetic acid, there is not many reports are there. It is mainly for our papers. There are some are still, I think, gold catalyst, but they are much poorer. So our catalyst gives much higher, proactivity, selectivity. So far, it is record. Actually, methanol wise, we are also, our catalyst is also the highest in terms of thermocatalyst, but there is one catalyst published using a MOP catalyst, that is the photocatalyst that is published in Nature Material a couple of years before. They have higher activity compared to ours. Okay, and I will take probably another 2-3 minutes. And besides methane oxidation, just I want to tell that we are also working for different kind of reactions for methane. Suppose if we convert methane CH to methane boron bond, then it will give the alkyl boronate esters. Like we use the aryl boronate or boronate esters for Suzuki reactions. So this is very important for many reactions as a synthetic intermediates. So if you convert the methane CH bond to CB, then it will give the methane boronate ester. And when we started the project for methane activations, like converting methane CH bond to methane boron bond, there are a couple of examples are there. And all catalysts were based on rhodium, iridium catalysts. Those are very prominent groups, Mendeleev's groups, Sanford groups, Lewis. They are all catalysts are basically the iridium catalyst or rhodium catalyst, and their turnover number is also very poor. So here definitely can we do the reactions with earth abundant metal, and we found that MOP is actually a very good material to stabilize the first flow transition metal even at high temperature because of the site isolations. For those organometallic or coordination compound, you cannot heat much because they will decompose. That is the problem that in all those catalysts, that's why they are giving the turnover number in very poor turnover number. But we found that if we develop in MOFs, then even fast transition metal complexes, they are very robust even at high temperature. So we did it with nickel, and we are very happy that we found that simple bipyridine, there is no fancy ligands. This is the MOFs, UIO-based MOF. It has the bipyridine linkers. We just metallated with nickel and with nickel hydride, and these catalysts efficiently convert methane to methane boronic ester, which is methane boronate ester. So these reactions happens at 150 degrees centigrade. And in our first shot, we got the turnover number up to 1400 turnover number. I'm not going to tell in details about the mechanism because I cut short everything within 30 minutes. I'm supposed to give it. And this catalyst can be also recycled. And recently we got a catalyst, it's not published. It can give a turnover number up to 12,000. And previously we can see that all the catalysts from the very prominent groups, their turnover number is like 50, 60. Mendeleev's group is producing up to turnover number to 2,000, but you cannot recycle that. Although it is heterogeneous, but you cannot recycle that. It's one shot, 2,000 turnover number. And our catalyst, we can recently got up to 12,000 turnover number. It's not published yet. And for that, I want to thank my group who did actually all the works. I think I did not do any reactions. This work primarily was done by Neha, who is now a postdoc at Professor Lehner Group at Next Maxland, and also the Mano, the coordinator research. And yeah, and also I want to thank ACRB, Gail in the beginning, Bio, for and I did for funding and support. And thank you so much. So question please, question from friend first.
First of all, congratulate you for excellent fundamental.
Oh, thank you. Thank you. Very speculative work, and many students are already working.
Yeah, I know that. One friends. Any questions? Even questions stupid, that is okay. Yeah, that's right. Obviously, good communication, that also proves it. But yes, talk about the mock P2P5. There you put that the temperature plays a role. You can't take the quantification as another. But can tell about the role of temperature. So what is why how the mechanics of the mechanical part is really important, you know, discuss details. So it is a plausible speculation about the temperature. So what we found that definitely look, this is a series activation. You group them in the other work, you know, that so high temperature you always accept it. But when you keep the yes, high temperature, there is also a problem overoxidation can happen. So overoxidation, because whatever the maximum acetic acid that not overoxidize. Very tricky reaction. There's a lot of reactions. We just found only the optimized conditions. In the optimized condition, temperature and time is also a matter. If we do the reactions in the extended time, then definitely ultimately you will get carbon dioxide. Surface is also a factor, and pore size is also a factor. So if you do the pore sizes larger or smaller, the diffusion is also a factor. If it is the very large, diffusion will be faster. If it is very large, then diffusion will be too faster. So it is all about the dynamics. So in the optimized conditions, pore size have to be very limited one. Not only for that, we've also found that product it also initially might absorb in the surface. Because if it's a high surface area, we found the overoxidation is less. So it is also known in heterogeneous catalysis that if it is high surface area, it actually decreases the overoxidation, probably absorb. Many times people also do the absorption study for heterogeneous catalysis. This is a kind of chemical loop that is called. Yeah, but this is a continuous one. So actually, so temperature is the two things, and for that particular process, we found that for lower temperature, methanol is fine. Acetic acid one, methanol is also the reactant. So methanol produces at 125. That methanol reacts and further reactions with insignificant CO, right? And then it gives to the acetic acid because acetic acid becomes physically and methanol really high temperature.
Stability is an issue. Most of the mechanism which you say, also we also do sometimes with I think some of the things we get the intermediate, some is speculate. That's why we like plausible mechanisms. Yeah. So what is your take? Because mechanistic inside this form is tricky. So what do you think about it?
Look, mechanism we have to study because whether in heterogeneous catalysis, first of all, the first question will come, does it matter? And what is the catalytic development? In homogeneous, it cannot do this reaction. These reactions, it cannot do any because above 100 bits centigrade, most of the homogeneous chemistry is that. Okay. So because of the site isolations, it is quite lower. So first our experiment is that before we study the mechanism that whether our catalyst is still intact or not. Our speculation is that yes, it should be because of the site isolations, but it is really yes or no. And we found it is yes. Even after 5 recycling, we take the powder XRD that shows the MOF is, that is fine. And also we studied the XFs also, and also for other XPS, all things, so whether in nanoparticle is forming or not, it may be possible, but we normally don't find. There are many recycling after that. When we saw that it started to degrading, we found that MOP is degrading, and some cases it's the leaching factors. It may be possible. Leaching.
Sorry,
Yes.
we are running out of time. Actually, we have an NMR session. There is a high tea. So students, please grab him because he's a local person. So until he answers your question, you will not allow him to go to metro, okay? So just you can grab him. So our next speaker is Professor Deepak Chopra. And he does not need any introduction because he's a leading expert in chemical crystallography and solid state chemistry. So there is already shortage of time, so I will not. So please start and next. Yeah.
My slide, so identify the student or download to the folder. Good afternoon, everybody. So I once again thank okay. Oh, so I once again thank the organizers. It's okay. I can use this one. I once again thank the organizers of this conference, particularly Ranjan, for the kind invitation. I also extend my heartiest thanks to ma'am for giving me this opportunity to come to this beautiful campus of Amity University. So I am a crystallographer by training, and I work on molecular crystals. And we have been also looking at applications of crystals to development of different kind of products. And there are two important things I work on. I work on pharmaceutical co-crystallization, where we are trying to engineer products, particularly drugs, which have got better physicochemical properties in terms of their biological availability, dissolution, and performance. And we also look at another aspect, which is like designing new electronic materials, particularly dielectrics. So there are two stories I'm going to discuss and keep it rather compact for all the students. First will be a discussion on the latest work we have done on co-crystallization in a drug, and another one will be looking at how certain inert substances can change crystal structures of very stable entities. So before we go into the details, I'll just give a very basic outline of what are co-crystals. So you have a compound which is a solid at room temperature. You can either crystallize the compound. These are single component or multi-components. In multi-components, you can have salts where you have two different components here which exist as salts, the positive and the negative charge. You can have a normal neutral co-crystal, and then you can also include solvents or hydrates to form solvatomorphs of these multi-component forms. Single component can give you different polymorphs, which are different crystal structures of the same chemical entity. And this is a very important classification because we keep this in mind when we design either new co-crystals with new properties or different polymorphs which can also have different properties. And because we have students here, I would like to emphasize that the crystal structure, when it is formed, it has a very basic component, that is hydrogen bonds. And traditionally, hydrogen bonds involve two electronegative atoms. You have here a donor side X and you have the acceptor side Y. And these interactions play a very important role in crystal packing. And the energetics are also variable. We can have strong hydrogen bonds to very weak spectrum of hydrogen bonds. And the role of cooperativity in crystal packing is also significant. In addition to traditional hydrogen bonds, we also have got pi-pi stacking interactions. We have the displaced pi-pi stacking, we have the phase co-facial stacking, and we also have the T-shaped geometry which are present in crystals. In addition to stacking interaction, we also have halogen bonds, where the halogens like chlorine, bromine, iodine in particular can form different kind of interaction motifs in the crystal packing. We have type 1, two types of type 1, and we have type 2 packing which govern halogen bond formation in crystals. Here you have to keep in mind that the halogen bond has got a amphoteric identity. You have a sigma hole which functions at the electrophilic center, and you also have the lone pair density which functions as the nucleophile. And based on the approach of the electrophile and the nucleophile, the corresponding aggregation takes place in molecular crystals. Polymorphism is a very interesting aspect in drug formalism, and this is a compound which is known as ROY. It's actually a carbonitrile derivative of thiophene and containing a nitro group. It tends to form large number of polymorphic modifications. It holds a record, world record, in fact, for the largest number of polymorphs. Polymorphs are characterized by different morphologies, different crystal structures, different melting points, and different torsions. For example, with respect to this bond theta, you can have different torsions, and this essentially classifies as polymorphs. So, and you also can have conversion of polymorphs from one form to another using melt crystallization techniques and so on and so forth. So with this background in mind, I would also like to emphasize that now you would like to form multi-component crystals. To form multi-component crystals, you need to break the existing hydrogen bonds in the structure and form new hydrogen bonds because you have two components. And at that time, you can either have the traditional acid-acid synthon, which is like homosynthon because you have the same entities. You can have an amide-amide synthon, but now you can take an acid and an amide and engineer a supramolecular heterosynthon, which can actually exist in a co-crystal. So you actually exploit these heterosyntons to form via hydrogen bonding to form new materials or new co-crystals. Now I will discuss about the latest work we have done in this anti-malarial drug called atavocone. So atavocone is marketed as a anti-malarial drug. It's a very potent anti-malarial drug. It's well known in the literature, and actually it's a PCS class 2 drug. It has got very poor solubility profile, and the purpose of working on atavocone was to improve the physicochemical properties like solubility, melting point, and chemical stability of this drug atavocone, so that we can have improved biological formulations of atavocone and we can administer atavocone in less quantities as well to the patients. And we can actually now use the concept of co-crystallization. We can actually make salts, co-crystals, and salt hydrates to get new crystalline formulations of atavocone. And as the parent drug exists as polymorphs, you already have two polymorphs of atavocone. One is a cis atavocone, where you see this phenyl group is cis to the planar system, and here it is trans. So these are called essentially the cis atavocone and a trans atavocone. And then the trans atavocone actually has two different polymorphs, which are shown as yellow and green respectively. So we call these conformational polymorphs because there are changes in conformation which accompany these polymorphs. So now the experiment was to grind these compound with co-formers. Now this co-former is not a random choice. These are generally regarded as safe. They should be safe. They should not be toxic. They should not be poisonous. You cannot take any co-former which has got a basic center which will form the corresponding co-crystal. You need to have them as non-toxic and non-poisonous. So these are defined by the pharmaceutical classification. So we can use these kind of heterogeneous bases like piperazine, dimethylaminopyridine, and 3,4-diaminopyridine. We actually do a mechanochemical grinding reaction which utilizes least amount of solvent, and we can do it at room temperature. And the most interesting observation here is that when you mix these two reactants, there is a change in color. So there is a dramatic change in color, telling you that is some kind of charge transfer happening when you grind the drug with a corresponding co-former. And when we did this grinding, the solvent we used to assist the process was methanol, and the ratio was 1:2. You can optimize this process with different combinations as well. First is to do the powder analysis. In the powder analysis, we can see that the product has been formed. The powder pattern is different for the co-crystals compared to that of the starting materials. So that's an initial signature. And then we crystallize this powder in different solvents. And when you crystallize it, for example, in 80 pp, we have got two polymers now. You can see the concomitant polymers. They exist here with different colors. When you do it in toluene and chloroform, in ATDM powder, you again get ATDM1, ATDM2, ATDM3, three different polymers. And in case of dimethylaminopyridine, you get the corresponding only one polymer. So you get this kind of interesting crystals. Now the next challenge is to determine the crystal structures. Now here I would like to put a word that these structures are not so easily determined. They're quite challenging, quite complex. These are very thin crystals. They're also very unstable. Over a period of time, they tend to take up water as well and dissolve. So we have to determine the structure in a certain frame of time. And now you can see here that the crystal structure has been determined. The challenge in crystal structure is to map the proton because we have got a OH group here. And as you can see, the proton here has been transferred to the corresponding nitrogen. This forms a NH2 plus. So this leads to the formation of a salt. You have a salt. This is the anionic part. This is the cationic part, and you have strong hydrogen bonds which are present. And you have got two polymorphs here. This is a 2:1 stoichomorph, and this is a 1:1 stoichomorph, where you see the full molecule of the base. And again, there has been a proton transfer at one nitrogen. The other one is still unprotonated. So this is a very careful crystal structure determination, and you can monitor this by looking at the bond lengths before deprotonation and after deprotonation. So what happens after deprotonation is that these bond lengths become more symmetrical. The carbonyl group, which was 1.22 angstrom, now becomes 1.26. Okay, because there is extended delocalization here. So initially it was carbonyl group, but now there is CO minus, so there is extended conjugation. So these tend to become similar in terms of their bond lengths. So you see the dramatic changes in geometry when the salt formation takes place in the formation of the co-crystal. So you can characterize these with very high accuracy. And then interesting thing is to look at the packing. Now in the packing, you have two different kinds of hydrogen bonds. One is the salt, where you have the proton transfer, and the other is you have the traditional NHO hydrogen bond. So both the green regions and the red regions are shown here, and you can see very clearly that you have the drug molecules which are connected in the presence of the co-former. This is the first polymorph. This is the second polymorph. You can see that the densities are very different. One is 1.3, another is 1.4 gram per cc. And these are the spectrum of hydrogen bonds. You look at the hydrogen acceptor distances, quite short, and the directionality is also there, which are classical of hydrogen bonds. You also have weak CHO hydrogen bonds, which are present, which stabilize the packing. Now we do careful thermal characterization experiments because we would like to see what happens to these crystals when you heat them. Because thermal stability is important, melting point is important. The melting point of the co-crystal is different from that of the drug, whether there are any solvent losses. So you do a tandem thermal characterization. We have, I presented here TGA data, I presented here the DSC data, and you can also see the hot stage microscopy data where you can map at every region what is the corresponding stage the crystal is in. So here you can see that there is a onset peak, and then you have the melting, and then you can actually again cool it. And at the corresponding temperature, is there any loss in mass? Because you can have decomposition, so that can reflect the thermal stability. And we have done this for both the polymers of ATPP, and you can see here that before it melts is a possible phase transition, as you can see here as well as here before it melts, and the melting point is 209 and 190 degrees. So the melting points of the two polymers are also different. Now we take the next polymorph, next stoichomorph with another coformer. Now this is a pretty complicated structure. What is interesting to the chemist is that I took ATDM, I took toluene, but I did not take water. Now water has been taken up by the compound during the process of grinding. And I started with a 1:2 ratio, but the final crystal structure has a 2:2 ratio. And then there is one equivalent of toluene. Toluene was used as a solvent of crystallization, and water has been picked up from outside, which is a fractional number. And you can see it's very complicated here because you have the drug molecule, you have another drug molecule. This is my toluene molecule here, and this is my water molecule sitting here, and these are extensively hydrogen bonded. So there is a lot of hydrogen bonding which happens here between the drug molecule and my coformer as well. So you can see here, this is extensive hydrogen bonding, and this gives you the solvate hydrate. And this is the packing again. You can see the packing very clearly. You have the drug molecules, and you have the coformer which is sitting in between. You have the water molecules which are forming the hydrogen bonds. So these nice, robust crystalline structures are formed. And this is the second polymorph. In the second polymorph, again, now you can see the first. This is the first molecule with the first packing with the water molecules. This is the same packing with the toluene molecules. You can now see the toluene molecules which are present. You can see here, these are the toluene molecules which are present. I think these are the toluene molecules which are present. And then Again, we can do the thermal characterization. You can see that there are complex events before the melting happens at 217 degrees centigrade. So there are solvent losses. You have toluene loss, you have water loss, and there is continuous loss till the crystal finally melts. That is the anhydrous form. And the experimental weight loss and the calculated weight loss match quite well with each other, indicating stability and after desolvation. And then the third one we got was the diaminopyridine with ethanol, where we get these ethanol molecules here. Now, one ethanol molecule is ordered, another is disordered. There again is you can see that there is a proton transfer. So this is the diaminopyridine. So this nitrogen is protonated, the OH is lost here. This forms strong charge assisted hydrogen bonds, making this new co-crystal entity. So this is essentially a salt solvate. So this is the packing of the molecules, where you can see the disordered solvent molecule, you can see the hydrogen bonding between the drug molecules, and you can also see the coformer. This is the coformer diaminopyridine, which is protonated at this particular site. So this nice crystal packing, which is crystalline, is also formed. This is the corresponding thermal characterization. Again, there is a phase transition here, and there is also solvent loss, and then there is final melt with decomposition. So when it melts, it also decomposes. So this is thermal stability is reduced for this particular co-crystal of atobacone. So these are some of the interesting results we have on atobacone, and we are trying to see whether any one of these can be made a popular formulation in the market and can replace atobacone. So we have got more, multi-component forms. I've just showed some of them, but as of now, we have more to be characterized, but definitely this will become more interesting in the nearby future. Another story I would like to tell you, this is very interesting for all of us. So we all work with silicon oil in the laboratory. We use silicon oil for mounting crystals. So when you take your crystals, you put it in silicon oil and you would like to mount it for diffraction. So what my student did was that he put this particular compound. So we actually may work on different kind of organic scaffolds, and he had taken this compound and he had put it on the silicon oil, and he went to the washroom and he came back. When he came back, he saw that his crystals have converted into needles. So he was surprised. He was thinking somebody has replaced his crystals with something else. So we did not know what has happened actually. Now this is very interesting for all of us, because today also we don't understand why it happened, that silicon oil is an inert and unreactive substance. Thousands of compounds have been mounted on silicon oil. This was the first case where it underwent a phase transformation into a completely different form at room temperature in the presence of silicon oil. So we were very interested to look at the mechanism and all these things. And so there are two compounds here. You can see here we have a ethanol group, and we have here two molecules where R1 is orthofluoro and the second one is metafluoro. And in both these cases, we saw this transformation taking place. Let me see whether this works here or not. Oh, it works. So now you see, this is what happened when he came back. He saw these needles coming out in silicon oil at extremely fast rate. So he did not know what has happened. How did I put in silicon oil? It is supposed to be inert, unreactive, but it has now transformed into a completely needle form. The plates have been transformed into the needle form. So you can see here in the orthoisomer, it has converted from form 2, which is the plate form, within a matter of say 1 hour, and within 6 hours, it has been completely converted. For the meta form, it was slow. He started at 2 p.m. post lunch, and till day 4, we monitored the rate of conversion, and we saw that the transformation has been completed. That means the kinetics is different, but the conversion has definitely happened. And now you can see very clearly the crystal structure. There are two molecules in the asymmetric unit. This is the orthoisomer. In silicon oil at room temperature, it is converted into this particular form. For the meta-isomer also, there has been a conversion in silicon oil from one polymorph to the other. So these were the two very interesting observations in silicon oil. And the next thing was that we did a lot of other experiments with other oils. We took mustard oil, we took other kinds of oils available in the market. We took pentane, cyclohexane, ethylene glycol, everything we tried, it did not work. It was very specific for silicon oil only. So we spent quite a bit of time trying to do large amount of oils and acids, fatty acids and all, melting them, putting our crystals, all those experiments did not undergo any transformation. It was very specific for this. So so we also do a DSC characterization where we would like to look at the melting points. The melting point for form 2 and form 1 are different, and same for the meta isomer. In the case of meta isomer, there is a phase transition before it melts, which corresponds to the form 1. You see it is converting here into the corresponding form 2 is converting into the form 1. It is the same melting point as that of the form 1. And this can also be done using heat. So on the diffractometer, if you put the crystal, the orthoisomer, and you heat it, it undergoes the same conversion like it happened in presence of silicon oil. So both heat and chemical stimuli can actually convert the orthoisomer one form to the other polymer. And in the case of meta, also the same thing happened. There was a phase transition into a form 1 at higher temperature. You can see very clearly from hot stage that if you start with form 2 crystal, you have a new phase which is formed there. This is the transparent crystal. You see the new phase forming, and after some time the new phase is completely converted. So this is called nucleation and growth phenomena. You have a new phase nucleating and completely converting into the new phase at the expense of the old phase. And then they both melt at the same temperature because now it has converted into form 1 from form 2, and both of them melt at the same temperature. Now, because there is a solid state phase transition before melting, we stop the experiment before melting and reverse the DSC cycle to cooling. When we did that, we observed a new phase which we called as the 1D phase, which is having a slightly different structure from the, it should convert into the form 2, but it actually went into another phase which is form D when we cooled it. So we were not able to capture actually the form 2, which should have happened, but we ended up with a different phase. Now look at the dramatic change. So the initial phase is a pi-pi stacking. You have two different molecules in the asymmetric unit, so the color is different. And in silicon oil, it forms the double sandwich herringbone structure. So this is the double sandwich herringbone structure on the right hand side. So there's a dramatic change in the structure. Within a matter of few minutes, the structure is completely transformed from the layered stacking to the double sandwich herringbone stacking. And in the case of the meta isomer, you can see that the chains are NHO this type, but in the presence of silicon oil and heat, as I told you, they convert into the form 1. This is the form 1 here. This is the different form. And form 1D, where now the chains are, so in case of form 1, you can see the layers are parallel. You can see the arrows are parallel, but here they are anti-parallel. So it's just a reversal of the arrangement of the NHO chains. Rest of the structure is comparable. And we wanted to give a mechanism where we propose this conversion. So there are two aspects: how the new polymers form and what is the role of silicon oil. So rotational motion of the molecules takes place. So you have here the form 2, and then this is an intermediate configuration we propose because the form 1 has got this slightly rotated molecule in the center, which corresponds to form 1 here. And then a further slight rotation corresponds to the form 1D. So the arrangement of molecules is in form 1D and form 1 is related to the intermediate configuration from form 2. So there is a relationship of that you can have molecular rotation, which is allowed because it does not take much energy to rotate the molecules relative to each other, maintaining the hydrogen bonding framework, and that degree of freedom is there to allow us to access other polymers as well. But now coming to the silicon oil, why did this happen? So this is the silicon oil. Now the challenge with silicon oil is that it is marketed by Sigma. They don't tell us molecular weight. So we don't know what is the N. They only tell us the average molecular weight, and we don't have other knowledge about the silicon oil which is being marketed. They have different grades of silicon oil. But then the idea was that we looked at the something called the BFDH morphology, where we construct the morphology of the crystal. And what we saw is that you have these hydrophobic groups which are exposed here. Now, when the hydrophobic groups are exposed, we know silicon has got vacant d orbitals, or they've got vacant orbitals. And we also have the ethanol group. So the ethanol group has got unsaturation. So it's the coordination of the unsaturated centers with silicon, which kind of triggers this silicon oil induced phase transition, where it goes from the layered structure to the double sandwich herringbone. And the same thing also happens for the other the meta structure, the meta compound, where you see again you have got these hydrophobic groups, which are again exposed on the surface, which actually interact with the silicon entity here and trigger the silicon induced phase transformation. So there is a role of unsaturation in the molecule, and where they are exposed, they are all exposed on the surface. So silicon oil interacts with the hydrophobic groups triggers a phase transition, and this process tends to be either fast for the ortho one, or it is even there for the meta one as well. So you need to see what is actually exposed on the surface. So that's it. I would like to complete my lecture, and I would like to acknowledge all the funding agency and initially ISC in the formative years of our institute when we had no facilities. Mohammed Shah, who did the work, Atobokon work, Bandari, and all the past students and postdocs, and my present students as well. And I thank you all for your kind presence.
I must say this is a very exciting talk from Professor. Now, any questions?
I remember Ranjan's student Anil should be here because he's exactly working in Teva, the part-time student of Ranjan, to make soluble crystals. Co-crystals.
So we have my actually, if you see my abstract, I thought I will give it on chlorpropionamide, but chlorpropionamide is done and published. I can send it to you. We have done animal study also there. This was the latest results, and because malaria is a threatening disease, so and atobocone is untouched. Till now, there is no literature on co-crystals of atobocone. So we are the first ones who are actually working on that.
Yeah, thank you, Professor Chopra. Wonderful lecture.
Thank you. Thank you very much.
It gives me that memory of my PhD days, similar structure or tape structure, etc. My excellent work on silicon oil. Can this concept be applied to other crystals?
We are now screening large number of crystals, and we are getting more and more results. So my latest work I would like to mention, we published last week in Communications Chemistry, Nature Publishing House, without any APC, and article processing charges. Those compounds have slightly different scaffolds. So they have an imine, those are benzimidamide. So they have C double bond and an NH2 and phenyl. They are again undergoing same silicon-induced phase transformation and leads to. So I told my peers, see, we have studied everything is inert, this is inert, that is inert. No, it is very specific. There are, interestingly, in solution, you can have diffusion process. In solid state, you have crystals, these are solid entities, blocks. You put it in silicon oil, inert, it has transformed completely. This is something unprecedented. That means now, if you use silicon oil, you have to be careful whether your compound has transformed from the solid state perspective or dissolved.
More about collaboration. I was thinking that we have just started with Dr. Arun in the liver cirrhosis and liver regeneration. Very less work has been done. So can we think about that co-crystal? We have Animal House. We will develop the models.
Which molecules are potent?
Yes,
then
we can do.
Engineer co-crystal.
Engineer them, and then we can do the in vivo, in vitro as well as in vivo.
Yes, I have done it for chlorpropionamide. This is a very challenging system, to be frank, because the stability is an issue. But one formulation is very stable, and I think I will leave it for the industry or you to take it up in future. It will be published soon, this one.
But you have gone to the in vivo system also?
No, this work we could not, because the structural work was very challenging. Student was masters. He wanted to complete. So we finished the work and it is almost through. But somebody can take up for the animal studies, the atobocone. We have not done anything.
Okay, so I'll be very happy to collaborate.
And I would love to do some collaboration, because I think one formulation can be very potent.
Okay.
Out of these 5 or 6 formulations, one formulation can be very potent, which is the stable one.
Yes, something we do together.
It is easy to administer.
Yes.
So it can dissolve better compared to the neutral drug.
So we have to see both
And
the
you
in
can
vitro
opt
as
the
well as in
dosage
vivo.
actually you give for achieving a certain IC50 value. For
But does the IC50 value changes when you go from the 2D to 3D microenvironment?
So that's what you have to measure. What is
What
the
you have to take.
IC50 value?
Because
So
if we
compared to
can,
the parent drug, what it is, it should improve. It should become lesser to achieve the same activity.
Yeah.
And salts should make it happen, because these are salts and they all form salts. So interestingly, that OH proton phenolic, which is actually doubly bonded, is easily lost in this environment.
Okay.
You don't have to do much. Simply mechanochemical grinding, proton
And
transfer.
then go.
You don't have to use any strong base. The co-former is the base,
Okay.
with which it hydrogen bond.
Okay.
And when these go, they modulate the hydrophobic hydrophilic balance at the cell wall.
Yeah.
And that provides the enhancement in solubility, or
Solubility.
dissolution. And that is how pharmaceutical
So
co-crystals
Ranjan,
are
if you
very interesting.
Ranjan should
So this
connect
is a
with
very
you.
big area.
and do
Professor
this.
Ashinangia works on this.
Yes, yes.
He's a pioneer. Professor Desiraju has already
Mostly, yes, we Fundamental science, we are doing very good. That should be done by the chemist. But we should also think about the technology transfer and some work we can do together as per our
This is
PMO's
one now-
Atmanirbhar Bharat.
This is not being pursued much in our country.
Yeah.
Pharmaceutical focus.
So I would request if you want to
Yeah.
collaborate with
In
us.
fact, I think this is something which your students can do. I can train.
Yeah, yeah.
I don't need my students. To
Thank
be
you.
frank with you.
Thank you.
Absolutely changing, transformation.
Now, this is because these bonds are very weak in this one form, and it will convert it to. But if I able to put some group that can able to make a very strong bond, that may not be able to do the phase transformations.
So we have strong hydrogen bonds here, as you see. NHO hydrogen bond is maintained.
Yeah.
But what happens? You have a chain. Now you need to herringbone packing. All you need to do is do a rotation. And that's what happens in solution. There's a rotation. Rotation does not need much, there's not much barrier to overcome. So rotation is possible, maintaining the hydrogen bonding framework. So you have strong hydrogen bonds, they are maintained, but the relative orientation switches fast. And that can happen because silicon is interacting with these exposed groups, and we then we really do not know how this process happens. We are only saying that this is what has happened, but how it does it very fast, we don't.
Because in some cases we have a very strong pi-pi interaction, some cases we have a hydrogen bond interaction.
You will not disturb much of these energetics because differences in lattice energy in polymers is very small.
Yeah.
Okay, so even they will maintain the integrity, but it is the overall packing which is transformed, mediated by silicon oil. So there is a role of silicon oil in triggering this process and achieving another stable aggregate of molecules in a certain period of time.
Okay, thank you.
The silicon oil experiments are still.
So any question from the students? Okay, think for 30 minutes and grab him in the NMR session, okay? So now when you want to hand over the mementos and certificate to the speakers, I request Professor Mukherjee and other faculty members to come here. And Dr. Also Kuntal Manna, please come and Professor Mukherjee will. It is really an exciting session overall. Like I must say, the diversity of the research topic and student must get the benefit also, right? No questions from student. So first, Professor Mukherjee will hand over to the Dr. Kuntal Manna. Please clap your hands. So now it's Dr. Pooja's turn to IISc to IISc around his. Please. Now, actually, we are at the very end. So now I'm requesting Professor Mukherjee to make a conclusive remarks and vote of thanks for this conference to announce the ending of this symposium.
Although I should not tell the vote, I should not give the vote of thanks at this moment, because if I tell vote of thanks, then founder president will not be okay with that, because one session will be there from 4 p.m., the inaugural session for our state-of-art NMR facility. So for the last vote of thanks for this session, I must thank all the speakers to make their time and come here and enlighten us with their innovative research work. And we see really a diversity of research in this first and second sessions. We thank all of you. Please stay in touch with us, collaborate with us. We are happy. We are always forward towards collaboration because we build in teamwork, and let us make India proud. So that's all. And also another thing, since Click Chemistry is a new institute, and most Amity chemistry department is renowned under applied science. Whenever you go back to your institute or you go to Japan, please do showcase us about Click Chemistry so that this Click Chemistry Institute gets renowned everywhere. Thank you so much.
पे करूं बच्चन पे करूं?
ऑडी पे सर, ऑडी पे सर।
क्या है ऑडी?
@amity.edu।
ये जो मेल का सब्जेक्ट है ना,
यस सर।
यही कर दो बस।
ठीक है सर।
ठीक है,
2 मिनट से भी करके दिखाते हैं आपको।
तो बस ध्यान रखना, जब फाउंडर सर जैसे ही इशारा करेंगे वैसे ही क्लिक करना है।
यस सर।
सर सर कर दिया हमने, सेटअप कर दिया है।
नहीं मैं यहीं पे हूँ सर, वो लगवा रहा हूँ बस, वो उस पे वो टेक्स्ट भी तो देना पड़ेगा ना
सर। टेक्स्ट आपकी मेल पे दे दिया है, जो मेल पे आपने लिखा है ना कि इनॉग्रेशन ऑफ वर्चुअल वाला, वो ही हम लगवा रहे हैं, क्योंकि आप इतनी देर तक। ठीक है, ठीक है। होस्ट कौन है? होस्ट
संजीव सर। गुड इवनिंग, संजीव बोल रहा हूँ मैं सर।
हाँ संजीव
जी सर।
ध्यान रखना है, जैसे ही फाउंडर सर इशारा करें वैसे ही
सर।
बटन दबाना है, उससे पहले बाद में नहीं।
ठीक है सर।
ठीक है,
ठीक है सर।
ओके। हाँ देवेंद्र जी।
हाँ जी सर।
मैंने वो सेटअप करा दिया है, तो फाउंडर सब सर जैसे ही इशारा करेंगे यहाँ से हम क्लिक करके उसको इनॉग्रेट कर देंगे।
अच्छा, वो भी मैं यहाँ पे अरेंज कर रहा था, वो नहीं करूँ फिर मैं?
क्या कर रहे थे आप अरेंज?
वो एक उसमें पीपीटी की एक स्लाइड बना रहा था।
नहीं, हमने बना दिया, हम यहीं से कर देंगे।
अच्छा, तो फिर फाउंडर जैसे मतलब फाउंडर जैसे हम कहेंगे क्लिक करने के लिए, वो क्लिक करेंगे और वहां से हो जाएगा आपके यहाँ पे।
हाँ, बट फाउंडर डमी क्लिक करेंगे।
हाँ, तभी क्लिक करेंगे ना।
हाँ, असली क्लिक इधर से उस पीसी पे होगा ना, जिस पीसी पे है।
ठीक है।
ठीक है,
तो सर वो मुझे स्लाइड मिल सकती है अगर जस्ट अगर मैं देखना फाउंडर को एक बार या नहीं?
हेलो बच्चन। हेलो।
यस सर।
बच्चन, मैंने तुम्हें को होस्ट बना दिया है, ठीक है?
क्या बना दिया सर?
को होस्ट बनाया है तो मैंने तुम्हें।
ठीक है सर।
ठीक है, स्पॉटलाइट का देख लेना कैसे करना है ना तुम्हें।
सर 1 मिनट अभी बात कराता हूँ।
ठीक है।
संजीव सर।
हाँ जी।
सर स्पॉटलाइट ना आप ही करना है, आपको ही।
नहीं, किसको करना है? मैं स्पॉटलाइट अभी तो इनको कर रखा है मैंने, वर्चुअल इनॉग्रेशन को।
जो सर ये वर्चुअल इनॉग्रेशन कैमरा है ना,
हाँ
इसको आप स्पॉटलाइट करके रखना।
हाँ, यही है। ठीक है।
यस।
ठीक है। लाइव कर दे लाइव
All the faculties, please come forward. And the coordinators. Where is Seema ma'am? All the coordinators. Ranjan, Shekhar,
How do you sequence? Yes. First week of the experiment go.
Or you can speak. Vivek?
Okay. After cutting this ribbon, then they will enter inside, and inside they will brief about that.
না না আমি বুঝতে পারছি। Should we start? Dr. Jasleen है यहाँ पर? Professor Shah? ये बोली ना?
उनका आया स्पीकर उनका नाम इंट्रोड्यूस कर दीजिएगा। हाँ
H fruit. नाम पूरा बड़ा था। Furuta. H Furuta. Professor Furuta. Welcome all for the congratulations. State of art facility. Strict chemistry developed and developed in the university. We have today.
With the name Amita.
Sir, multiple instrumentation capacity analysis. Come to the evening for which we were waiting for months after instruction at an international symposium on environmental chemistry with 4 guests. Which we never from the
You can go. Okay. We keep one of those professors sick.
Yes, yes.
Yes. Mona Lisa, you come here.
ये गाना बनता है Kanam sir and Akhil sir is also there. Oh.
Nice to meet you.
I did that. The instruments for testing. I'm good. Yeah, testing and Amita. Wow, very nice. Amita. Yeah,
Or the strongest.
Yes, sir. After long times. Lot of, I do remember, we were going here and there, all the blocks to find out the rules.
Waiting for you, then everyone has joined to support.
It's always a teamwork.
Yeah.
I used to bother so much everyone. I had liquid nitrogen generator. Yes.
Last week
Once we have once in a week. We always provide nitrogen on 50 to 52 and 55 because per and give the prediction of the molecular structure of a compound.
I have my
जब आप रैंप लाइटिंग करेंगे रैंप लाइटिंग करते हैं सरस्वती वंदना बोलते रहेंगे तो इनको ये लैंप लाइटिंग के साथ होना चाहिए
What is Radhika?
slowly melody
বাজনাও চলে যাচ্ছে কতবার যে রিজাইন করেছে এখান থেকে আর কতবার যে
অনলাইন ওল্ড waiting for whatever powder to join so actually it will come on the screen पता चलता है
जल्दी बोलिए because
शर्मा जी प्लीज सपोर्ट Thank you very much. Thank you, sir. Thank you, Dr. Yeah, all the Thank you.
Thank you, sir. Thank you, sir.
अभी sir, we are trying for a faculty and from
हमेशा